In the blink of an eye, a single event in the farthest reaches of the universe can release more energy than our sun will emit in its entire lifetime. This is the power of a gamma-ray burst, one of the most explosive and mysterious phenomena in the cosmos. Imagine a beam of light so intense it outshines entire galaxies, traveling billions of light years across the universe to reach us. These bursts are not just flashes in the dark. They are cosmic fireworks signaling the birth of black holes, the collision of neutron stars, or the death of massive stars. Yet, despite their incredible energy, gamma-ray bursts are fleeting, lasting only seconds or minutes, making them some of the rarest and most elusive events in the universe. Today, we're diving deep into the mysteries of these distant cosmic explosions, uncovering 50 astonishing facts that will change the way you see the universe. From their accidental discovery to their role in shaping the cosmos, get ready to explore the universe's most distant gamma-ray bursts and the secrets they hold. Stay with us because what you're about to learn will leave you in awe of the vast, mysterious, and ever-expanding universe we call home. Now, let's step back in time to uncover how humanity first stumbled upon these cosmic marvels. The story of gamma-ray bursts begins not in a high-tech observatory, but in the midst of the Cold War. In the 1960s, military satellites designed to monitor nuclear tests on Earth detected something unexpected: brief, intense flashes of gamma rays. At first, scientists were baffled. Could these be secret nuclear explosions? The idea was alarming, but as more data came in, it became clear that these bursts weren't coming from Earth. They were originating from deep space, far beyond our solar system. This accidental discovery marked the beginning of a new chapter in astronomy. For the first time, scientists realized that the universe was capable of producing such unimaginably powerful events. This revelation didn't just solve a mystery, it opened up a whole new field of study, reshaping our understanding of the cosmos and proving that even the most advanced technology can stumble upon the universe's greatest secrets. Now let's turn our attention to the sheer power behind these cosmic explosions. Gamma-ray bursts are not just powerful, they are unimaginably energetic. To put it into perspective, the energy released during a single gamma-ray burst can outshine the entire output of our sun over its entire lifetime. That's right, in just a few seconds or minutes, a gamma-ray burst unleashes more energy than our sun will produce in 10 billion years. It's almost impossible to wrap your head around, but think of it this way. If you could somehow harness the energy of a single gamma-ray burst, it would be equivalent to detonating billions of atomic bombs simultaneously. This staggering concentration of energy makes gamma-ray bursts the most powerful events in the known universe. And yet, despite their incredible intensity, these bursts are fleeting, lasting only moments before fading into the cosmic background. This combination of immense power and brevity is what makes gamma-ray bursts so fascinating and so challenging to study. As we continue to explore these cosmic fireworks, we're reminded just how dynamic and explosive the universe truly is. Now, let's dive into the fascinating world of gamma-ray bursts and uncover the two main types that scientists have identified. Gamma-ray bursts are broadly categorized into long-duration and short-duration bursts, each with its own unique characteristics and origins. Long-duration bursts, as the name suggests, last anywhere from a few seconds to several minutes. These bursts are often linked to the dramatic collapse of massive stars, known as hypernova, which occur when a star many times more massive than our Sun exhausts its fuel and collapses under its own gravity. The result is a spectacular explosion that sends out intense gamma rays, marking the birth of a black hole. A famous example of a long-duration burst is GRB 970508, which lasted for over 30 seconds and was accompanied by a visible supernova, providing strong evidence for this connection. On the other hand, short-duration bursts are much briefer, typically lasting less than 2 seconds. These bursts are thought to originate from the collision of two incredibly dense objects, such as neutron stars or a neutron star and a black hole. When these objects spiral toward each other and merge, they release a tremendous amount of energy in the form of gamma rays. One of the most well-known short bursts is GRB 050509b, which lasted just a fraction of a second and was later linked to the merger of two neutron stars. This discovery was groundbreaking, as it not only confirmed the origin of short bursts, but also provided the first direct evidence of gravitational waves, a phenomenon predicted by Einstein over a century ago. While both types of bursts are incredibly energetic, they differ in their energy outputs and afterglows. Long bursts tend to release more energy overall, but their afterglows are often easier to detect, lasting for days or even weeks. Short bursts, while less energetic in total, pack their energy into a much shorter time frame, making them harder to observe. However, their afterglows, when detected, can provide crucial insights into the environments where these mergers occur. Understanding these differences helps scientists piece together the life cycles of stars and the violent events that shape our universe. As we continue to explore these cosmic phenomena, we uncover more about the forces that drive the universe's most powerful explosions. Now, let's take a closer look at the powerful connection between long gamma-ray bursts and supernova. When a massive star reaches the end of its life, it doesn't go quietly. Instead, it undergoes a catastrophic collapse, leading to one of the most energetic events in the universe, a supernova. But in some cases, this collapse doesn't just produce a supernova, it also triggers a long gamma-ray burst. This happens when the core of the star collapses into a black hole and the surrounding material is ejected in a highly focused jet of energy. The result is a dual cosmic spectacle, a supernova and a gamma-ray burst occurring simultaneously. Scientists have gathered compelling evidence to support this connection. For instance, in the case of GRB 970508, astronomers observed not only the gamma-ray burst but also the telltale signs of a supernova in the same location. The burst was followed by a bright afterglow, and within days the light from the supernova became visible, confirming that the two events were linked. This discovery was a major breakthrough, as it provided direct proof that long gamma-ray bursts are often accompanied by supernova. The relationship between these two phenomena is crucial for understanding the life cycles of massive stars. Supernova mark the explosive end of a star's life, scattering heavy elements like iron and gold into space, which eventually form new stars and planets. Gamma-ray bursts, on the other hand, offer a glimpse into the extreme physics at play during the birth of black holes. Together, they paint a vivid picture of how the universe recycles matter and energy on a grand scale. By studying these events, scientists can also learn more about the conditions that lead to the formation of black holes and the role of massive stars in shaping galaxies. The connection between long gamma-ray bursts and supernova is a reminder of how interconnected cosmic events are, and how one explosive moment can reveal so much about the universe's history and evolution. As we continue to explore these phenomena, we uncover new layers of understanding about the forces that drive the cosmos. Now, shifting our focus to a different kind of cosmic explosion, let's explore the mystery of short gamma-ray bursts. Unlike their long-duration counterparts, which are linked to the collapse of massive stars, short GRBs are thought to originate from the violent collisions of neutron stars or black holes. These events are incredibly brief, often lasting less than 2 seconds, but they pack an extraordinary amount of energy into that fleeting moment. One of the biggest challenges in studying short GRBs is their elusive nature. Because they last such a short time, capturing detailed observations is incredibly difficult. Additionally, many short GRBs don't leave behind a visible afterglow, which makes it harder for astronomers to pinpoint their exact location or study their aftermath. This lack of afterglow has long puzzled scientists as it limits the amount of information they can gather about these events. However, recent breakthroughs have shed new light on these cosmic mysteries. In 2017, a historic event occurred when scientists detected both a short GRB and gravitational waves from the same source. This marked the first time a gamma-ray burst was observed alongside gravitational waves, confirming that the collision of two neutron stars was the cause. The detection of gravitational waves provided a new way to study these events, offering insights into the extreme physics at play during such collisions. This discovery was a game-changer, as it not only confirmed the origin of short GRBs, but also opened up a new era of multi-messenger astronomy. By combining data from gamma-ray detectors and gravitational wave observatories, scientists can now piece together a more complete picture of these fleeting yet powerful events. The study of short GRBs continues to reveal fascinating details about the universe's most extreme environments, from the dense cores of neutron stars to the ripples in space-time caused by their collisions. As we uncover more about these enigmatic bursts, we gain a deeper understanding of the forces that shape the cosmos. The mystery of short GRBs reminds us that even the briefest events in the universe can hold profound secrets, waiting to be unlocked by the tools of modern astronomy. Now, let's turn our attention to one of the most fascinating aspects of gamma-ray bursts, the afterglow phenomenon. After the initial burst of gamma rays fades, what remains is a lingering glow that can last for days, weeks, or even longer. This afterglow, emitted across multiple wavelengths such as X-ray, optical, and radio, acts like a cosmic fingerprint, revealing critical details about the environment and distance of the burst. The afterglow is created as the high-energy jets from the GRB collide with the surrounding interstellar material, producing a cascade of radiation. This glow is much fainter than the initial burst, but is far easier to observe over extended periods. By studying the afterglow, astronomers can determine the burst's distance, the density of the surrounding space, and even the composition of the material it passed through. It's like piecing together a cosmic crime scene where the afterglow provides the clues. Telescopes like Hubble and Chandra have been instrumental in capturing these afterglows. Hubble's optical observations allow scientists to pinpoint the exact location of the burst, while Chandra's X-ray capabilities reveal the high-energy processes at play. Together, these telescopes provide a multi-wavelength view that helps unravel the mysteries of GRBs. For instance, by analyzing the afterglow, researchers have discovered that some GRBs occur in distant, star-forming galaxies, offering insights into the conditions that give rise to these explosive events. The afterglow phenomenon not only deepens our understanding of gamma-ray bursts, but also serves as a bridge to studying the broader universe. It's a reminder that even after the brightest flash fades, the story of these cosmic explosions continues to unfold, revealing secrets hidden in the faint glow left behind. Now, shifting our focus to a truly groundbreaking discovery, let's talk about GRB 090423, the most distant gamma-ray burst ever detected. This extraordinary event occurred an astonishing 13 billion years ago, placing it just 630 million years after the Big Bang. To put that into perspective, this GRB erupted when the universe was in its infancy, a time when the first stars and galaxies were only beginning to form. The detection of GRB 090423 was a monumental achievement for astronomers. It provided a rare glimpse into the early universe, offering clues about the conditions that existed during this formative period. By studying the light from this burst, scientists were able to confirm its staggering distance, making it one of the most distant objects ever observed. This discovery not only pushed the boundaries of our observational capabilities, but also deepened our understanding of how the universe evolved in its earliest stages. What makes this GRB particularly significant is its role as a cosmic time capsule. The light from GRB 090423 traveled across the universe for billions of years before reaching us, carrying with it information about the environment it passed through. This allowed researchers to study the composition of the early universe, including the presence of elements like hydrogen and helium, which were abundant during this era. It's like receiving a message from the dawn of time itself. The discovery of GRB 090423 also highlighted the incredible power of gamma-ray bursts as tools for probing the distant universe. These bursts act as beacons, illuminating the darkest corners of space and time. By studying them, we can piece together the story of how the universe grew from a hot, dense state into the vast, complex cosmos we see today. This record-breaking GRB serves as a reminder of how much we still have to learn about the universe's origins and the forces that shaped it. As we continue to explore the mysteries of gamma-ray bursts, discoveries like GRB 090423 remind us of the incredible potential of astronomy to uncover the secrets of the cosmos. Each burst is a window into the past, offering a unique opportunity to study the universe's earliest moments and the processes that set the stage for everything that followed. Now, let's dive into one of the most fascinating tools astronomers use to measure the vast distances of gamma-ray bursts: redshift. Redshift is a phenomenon that occurs when light from distant objects like GRBs stretches as it travels through the expanding universe. Imagine the universe as a stretching rubber sheet with light waves being pulled along with it. As these waves stretch, their wavelengths grow longer, shifting toward the red end of the light spectrum. This is why it's called redshift. The amount of redshift tells us how far away an object is. The greater the redshift, the farther the light has traveled, and the older the object we're observing. For gamma-ray bursts, this is especially important because it allows scientists to pinpoint their distances with incredible precision. For example, GRB 090423, the record-breaking burst we just discussed, had an extremely high redshift, confirming its place as one of the most distant objects ever observed. But redshift isn't just about measuring distance, it's also a window into the universe's history. High redshift GRBs like GRB 090423 give us a glimpse into the early universe when galaxies were still forming and the cosmos was much denser and hotter. By studying the redshift of these bursts, astronomers can map out how the universe has expanded over billions of years, shedding light on the forces driving this expansion, such as dark energy. One of the most exciting aspects of redshift is its ability to reveal the composition of the early universe. As light from a GRB travels through space, it passes through clouds of gas and dust, leaving behind absorption lines in its spectrum. These lines act like fingerprints, telling us what elements were present in the universe billions of years ago. For instance, high redshift GRBs have shown that the early universe was dominated by hydrogen and helium, the simplest and most abundant elements. Redshift also helps us understand the relationship between gamma-ray bursts and the galaxies they originate from. By measuring the redshift of a GRB and its host galaxy, scientists can determine how far the burst traveled and how long ago it occurred. This information is crucial for understanding the life cycles of stars and the conditions that lead to these explosive events. In the grand scheme of cosmology, redshift is more than just a measurement. It's a key to unlocking the mysteries of the universe's evolution. Each high redshift GRB we detect adds another piece to the puzzle, helping us build a clearer picture of how the cosmos has changed over time. As we continue to study these distant bursts, redshift will remain an essential tool, guiding us deeper into the history of the universe and the forces that shape it. Now, let's turn our attention to one of the most intriguing aspects of gamma-ray bursts, their connection to black holes. It's widely believed that many GRBs are born from the dramatic events that lead to the formation of black holes. Picture this: a massive star, many times heavier than our Sun, reaches the end of its life. As it exhausts its nuclear fuel, its core collapses under its own gravity, triggering a cataclysmic explosion. This collapse can result in the birth of a black hole, an object so dense that not even light can escape its pull. In the process, an enormous amount of energy is released, often in the form of a gamma-ray burst. But it's not just collapsing stars that can create these bursts. When two neutron stars, ultra-dense remnants of dead stars, spiral toward each other and collide, they can also form a black hole. This merger releases a staggering amount of energy, producing a short-duration gamma-ray burst. These events are so powerful that they can outshine entire galaxies for a brief moment, making them some of the most energetic phenomena in the universe. So, how do we know that black holes are involved in these processes? One key piece of evidence comes from the jets of particles and radiation that are often observed alongside GRBs. These jets, traveling at nearly the speed of light, are thought to be launched by the newly formed black hole. As matter swirls around the black hole in a disk, some of it gets funneled into these narrow beams, which are then blasted outward into space. When these jets are pointed directly at Earth, we detect them as gamma-ray bursts. The connection between GRBs and black holes is further supported by observations of gravitational waves. In 2017, scientists detected ripples in spacetime caused by the collision of two neutron stars. This event, known as GW170817, was accompanied by a short gamma-ray burst, providing strong evidence that such mergers can indeed produce black holes and GRBs simultaneously. Understanding this link between gamma-ray bursts and black holes not only sheds light on the life cycles of stars, but also helps us unravel the mysteries of these enigmatic cosmic objects. Each GRB we observe offers a glimpse into the violent processes that shape the universe, from the birth of black holes to the incredible forces at play in the cosmos. As we continue to study these events, we're piecing together a clearer picture of how black holes form, evolve, and influence their surroundings. Now, let's zoom in on one of the most fascinating features of gamma-ray bursts, their powerful jets. These jets are narrow, focused beams of particles and radiation that shoot out from the source of the GRB at nearly the speed of light. Imagine a cosmic fire hose blasting energy across the universe with incredible precision. It's these jets that make gamma-ray bursts so incredibly bright, even from billions of light years away. When one of these jets happens to be pointed directly at Earth, we see the full force of the burst, which can outshine entire galaxies for a brief moment. But what exactly powers these jets? As we've discussed earlier, many GRBs are linked to the formation of black holes. When a massive star collapses or two neutron stars merge, the newly formed black hole is surrounded by a swirling disk of superheated matter. Some of this material gets funneled into these narrow jets, which are then launched outward at nearly the speed of light. The energy packed into these jets is mind-boggling, often equivalent to the energy the sun will emit over its entire lifetime, all concentrated into just a few seconds or minutes. Observing these jets, however, is no easy task because they are so narrow and travel at such extreme speeds. They are incredibly difficult to detect unless they are pointed directly at us. Even then, the afterglow of the burst, the lingering light emitted as the jet interacts with surrounding material, can fade quickly, leaving scientists with only a short window to study them. To overcome this challenge, astronomers rely on a network of telescopes that can rapidly respond to GRB alerts. Instruments like the Swift satellite and ground-based observatories work together to capture the fleeting light of these jets across multiple wavelengths, from gamma rays to radio waves. One of the key techniques scientists use to study these jets is called polarimetry, which measures the polarization of light. By analyzing how the light waves are oriented, researchers can learn about the structure and magnetic fields within the jets. This helps them piece together how these jets are formed and how they manage to stay so tightly focused over such vast distances. The study of GRB jets not only deepens our understanding of these cosmic explosions, but also provides insights into the behavior of matter and energy under extreme conditions. Each jet we observe is like a cosmic laboratory, offering a glimpse into the physics of black holes, the nature of relativistic speeds, and the forces that shape the universe. As our technology and techniques continue to improve, we're uncovering more about these incredible phenomena, bringing us closer to solving some of the universe's greatest mysteries. Now, let's turn our attention to a crucial yet often overlooked player in the drama of gamma-ray bursts, magnetic fields. These invisible forces are not just bystanders, they are key architects in shaping the jets and energy release of GRBs. Without magnetic fields, the incredible precision and power of these jets would simply not be possible. Magnetic fields act like cosmic sculptors, channeling and accelerating particles to near light speeds. Imagine a powerful funnel guiding the chaotic energy of a collapsing star or merging neutron stars into a tightly focused beam. This process, known as magnetic collimation, is what keeps the jets so narrow and concentrated over vast distances. Without it, the energy would dissipate into the surrounding space, and we wouldn't witness the spectacular brightness of a gamma-ray burst. But how do magnetic fields achieve this? Recent research suggests that the intense magnetic fields generated during the formation of a black hole or neutron star merger play a critical role. These fields twist and coil, creating a sort of cosmic slingshot that propels particles outward. At the same time, they act like a lens, focusing the energy into a narrow beam. This dual role of acceleration and collimation is what makes magnetic fields so essential to the mechanics of GRBs. Scientists have also discovered that magnetic fields can influence the afterglow of a GRB. As the jet interacts with the surrounding material, the magnetic fields within the jet can leave distinct imprints on the light we observe. By studying these patterns, researchers can learn more about the strength and structure of the magnetic fields, providing clues about the conditions that gave rise to the burst. One of the most exciting developments in this field is the use of advanced simulations and observations to map the behavior of magnetic fields in real time. For example, recent studies using data from the Fermi Gamma-Ray Space Telescope have revealed how magnetic fields can fluctuate during a GRB, offering new insights into the dynamic processes at play. These findings are helping scientists refine their models of how GRBs work, bringing us closer to understanding the full picture of these cosmic explosions. The role of magnetic fields in GRBs is a reminder that even the most powerful events in the universe are governed by fundamental forces. By unraveling the mysteries of these fields, we're not only learning more about gamma-ray bursts, but also gaining a deeper understanding of the physics that shape the cosmos. As we continue to explore, each discovery brings us one step closer to unlocking the secrets of these extraordinary phenomena. Now, let's shift our focus to a question that might send a shiver down your spine. What would happen if a gamma-ray burst occurred close to Earth? While GRBs are typically billions of light years away, the thought of one happening nearby raises important questions about their potential impact on our planet. If a GRB were to occur within a few thousand light years of Earth, the effects could be catastrophic. The intense gamma-ray radiation from such an event could strip away a significant portion of our ozone layer, leaving the planet vulnerable to harmful ultraviolet radiation from the sun. This would not only increase the risk of skin cancer and other health issues, but could also disrupt ecosystems, affecting agriculture and marine life. The sudden influx of gamma rays could also ionize the upper atmosphere, potentially damaging satellites and disrupting global communication systems. But how likely is such an event? Fortunately, the chances are extremely low. GRBs are rare, and the probability of one occurring close enough to Earth to cause significant harm is minimal. Our galaxy, the Milky Way, doesn't have many of the massive stars that typically produce long GRBs, and neutron star mergers, which create short GRBs, are even less common. Additionally, Earth's atmosphere provides a natural shield, absorbing much of the gamma-ray radiation before it reaches the surface. That said, history does offer a glimpse of what even a distant GRB can do. In 2004, a GRB located about 2 billion light-years away briefly affected Earth's ionosphere. This event, known as GRB 041227, caused a sudden disturbance in the upper atmosphere, altering the propagation of radio waves. While the effects were minor and short-lived, they demonstrated that even faraway GRBs can leave a mark on our planet. Scientists continue to study the potential risks of nearby GRBs, using models to simulate their effects and assess the likelihood of such an event. While the odds are in our favor, understanding these cosmic threats helps us prepare for the unexpected. After all, the universe is full of surprises, and GRBs are a reminder of just how powerful and unpredictable it can be. As we move forward, let's explore another fascinating aspect of gamma-ray bursts, the search for their progenitors, the cosmic objects that give rise to these incredible explosions. Now, let's turn our attention to one of the most intriguing questions in gamma-ray burst research. What exactly causes these colossal explosions? The search for GRB progenitors, the cosmic objects responsible for these bursts, has been a major focus for astronomers. While we've made significant progress, the mystery is far from fully solved. Massive stars, particularly those that end their lives in supernova, are believed to be the primary sources of long-duration GRBs. When these stars collapse, they can trigger both a supernova and a gamma-ray burst, releasing an unimaginable amount of energy in the process. However, not all massive stars produce GRBs, and scientists are still working to understand why some do while others don't. This has led to the study of factors like stellar rotation, magnetic fields, and chemical composition, all of which may play a role in determining whether a star becomes a GRB progenitor. On the other hand, short-duration GRBs are thought to originate from the mergers of neutron stars or black holes. These cataclysmic events, which can also produce gravitational waves, are incredibly rare and difficult to observe. One of the most groundbreaking discoveries in this area came in 2017, when astronomers detected both a short GRB and gravitational waves from the same event. This marked the first time a GRB was directly linked to a neutron-star merger, providing strong evidence for this theory. The accompanying kilonova, a bright explosion caused by the merger, also offered valuable insights into the production of heavy elements like gold and platinum. Despite these breakthroughs, linking specific GRBs to their progenitors remains a challenge. Many GRBs occur in distant galaxies, making it difficult to identify the exact objects involved. Additionally, the brief nature of these bursts means that follow-up observations must be conducted quickly to capture any afterglows or remnants. This is where multi-messenger astronomy comes into play. By combining data from gamma-ray detectors, optical telescopes, and gravitational wave observatories, scientists can piece together a more complete picture of these events. Recent advancements in technology have also opened new doors for GRB research. Instruments like the James Webb Space Telescope and the upcoming Vera Rubin Observatory promise to provide even deeper insights into the origins of these cosmic explosions. As our tools and techniques continue to improve, so too does our understanding of the universe's most powerful phenomena. The search for GRB progenitors is not just about solving a scientific puzzle, it's about uncovering the fundamental processes that shape our universe. Each discovery brings us closer to understanding the life cycles of stars, the formation of black holes, and the origins of the elements that make up our world. And as we continue to explore, who knows what other cosmic secrets we might uncover. Next, let's dive into the critical role that satellites play in detecting and studying these elusive bursts, and how they've revolutionized our understanding of gamma-ray astronomy. Now, shifting our focus to the tools that make these discoveries possible, let's explore the critical role satellites play in detecting and studying gamma-ray bursts. Without these advanced space-based observatories, much of what we know about GRBs would remain a mystery. Satellites like Swift, Fermi, and Integral are at the forefront of this research, equipped with cutting-edge instruments designed to capture the fleeting signals of these cosmic explosions. The Swift satellite, for example, is a marvel of engineering. Launched in 2004, it's specifically designed to detect GRBs and quickly relay their positions to ground-based telescopes. Swift's Burst Alert Telescope can pinpoint the location of a GRB within seconds, allowing astronomers to observe the afterglow in X-ray, ultraviolet, and optical wavelengths. This rapid response is crucial as GRB afterglows fade quickly, and every second counts in gathering data. Fermi, on the other hand, specializes in capturing high-energy gamma rays. Its Large Area Telescope and Gamma Ray Burst Monitor work together to detect GRBs across a wide range of energies, providing insights into the most energetic processes in the universe. Fermi has been instrumental in identifying some of the most distant and powerful GRBs ever recorded, helping scientists probe the early universe and test fundamental physics. Integral, the International Gamma Ray Astrophysics Laboratory, complements these missions by focusing on lower energy gamma rays and X-rays. Its sensitive instruments allow it to study the fine details of GRB spectra, shedding light on the physical processes at work during these explosions. Together, these satellites form a powerful network, each contributing unique data that helps piece together the puzzle of GRBs. One of the most remarkable aspects of these satellites is their ability to respond rapidly to GRB events. When a burst is detected, alerts are sent out within seconds, enabling telescopes around the world to swing into action. This coordinated effort has led to some of the most detailed observations of GRBs and their afterglows, revealing information about their environments, distances, and origins. The importance of satellites in GRB research cannot be overstated. They provide a window into the high-energy universe that ground-based telescopes simply cannot access. By capturing the initial burst and its afterglow, these satellites allow scientists to study GRBs in unprecedented detail, advancing our understanding of these cosmic phenomena. As we continue to push the boundaries of space exploration, next-generation satellites and observatories promise to take GRB research even further. With improved sensitivity and faster response times, the future of gamma-ray astronomy looks brighter than ever. And as we uncover more about these distant explosions, we'll gain deeper insights into the universe's most extreme events. Next, we'll delve into the mystery of dark GRBs, those elusive bursts that leave little to no visible afterglow, challenging our understanding of these cosmic phenomena. Now, let's turn our attention to one of the most puzzling mysteries in gamma-ray burst research: dark GRBs. Unlike the bursts we've discussed so far, dark GRBs are enigmatic because they leave little to no visible afterglow. This absence of light makes them incredibly difficult to study, yet they hold crucial clues about the universe's most extreme events. So, what makes a GRB dark? One leading theory suggests that dust plays a significant role. When a GRB occurs in a galaxy filled with thick clouds of dust, the visible light from the afterglow can be absorbed or scattered, rendering it invisible to optical telescopes. This dust obscuration effectively hides the burst from our view, leaving only the high-energy gamma rays to signal its presence. Another possibility is that dark GRBs occur in extremely distant, faint galaxies. These galaxies are so far away that their light is stretched and dimmed by the expansion of the universe, making their afterglows nearly impossible to detect. In these cases, the GRBs themselves might be just as bright as their counterparts, but their afterglows are lost in the vastness of space. Studying dark GRBs presents unique challenges. Without a visible afterglow, scientists must rely on other wavelengths, such as X-rays or radio waves, to gather information. Satellites like Swift and Chandra are invaluable in this effort, as they can detect the X-ray afterglows that often accompany these bursts. Radio telescopes also play a critical role, as radio waves can penetrate dust and provide insights into the GRB's environment. One of the most intriguing aspects of dark GRBs is what they reveal about the early universe. Because many of these bursts are thought to occur in distant, ancient galaxies, they offer a glimpse into the conditions of the cosmos billions of years ago. By studying their properties, scientists can learn more about the formation of galaxies, the distribution of dust, and the evolution of the universe itself. Despite the challenges, researchers have made significant progress in uncovering the secrets of dark GRBs. Techniques like rapid follow-up observations and multi-wavelength analysis have allowed scientists to piece together the puzzle, even when the afterglow remains hidden. Each discovery brings us closer to understanding these elusive events and their role in the cosmic tapestry. As we continue to explore the mysteries of dark GRBs, one thing is clear: they remind us just how much we still have to learn about the universe. With every burst detected, whether bright or dark, we gain new insights into the forces that shape our cosmos. And as our tools and techniques improve, the secrets of these enigmatic explosions will slowly come to light. Next, we'll explore how gamma-ray bursts may have influenced the evolution of the universe itself, shaping the galaxies and stars we see today. Now, let's shift our focus to a fascinating idea that connects gamma-ray bursts to the very fabric of cosmic evolution. These powerful explosions may have played a crucial role in shaping the universe as we know it. One of the most intriguing theories suggests that GRBs could have contributed to the ionization of gas in the early universe, helping to clear the way for the formation of stars and galaxies. When a gamma-ray burst occurs, it releases an immense amount of energy, including high-energy radiation that can ionize surrounding gas. This process strips electrons from atoms, creating a more electrically charged environment. In the early universe, this ionization could have been a key factor in breaking apart dense clouds of gas, allowing them to collapse and form the first stars. Over time, these stars would go on to create the building blocks of galaxies, setting the stage for the cosmic structures we see today. Evidence supporting this theory comes from the detection of GRBs in young, star-forming galaxies. These galaxies are often rich in gas and dust, providing the perfect conditions for both GRBs and star formation. By studying the locations and environments of these bursts, scientists have found that GRBs are more likely to occur in regions where stars are actively being born. This correlation suggests a deep connection between GRBs and the processes that drive cosmic evolution, but the influence of GRBs doesn't stop there. Some researchers believe that these bursts could have also triggered star formation by compressing nearby gas clouds. The shock waves from a GRB's explosion might push gas together, increasing its density and making it more likely to collapse into new stars. This idea is still being explored, but it offers a compelling explanation for how GRBs could have acted as cosmic catalysts, shaping the universe on a grand scale. Understanding the role of GRBs in cosmic evolution is not just about piecing together the past, it's also about unlocking the secrets of the universe's future. By studying these bursts, scientists can gain insights into how galaxies form, how stars are born, and how the universe has evolved over billions of years. Each GRB detected is like a time capsule, offering a glimpse into the conditions of the early cosmos and the forces that have shaped it. As we continue to explore the mysteries of gamma-ray bursts, one thing becomes clear: these explosive events are more than just fleeting flashes of light. They are powerful agents of change, playing a vital role in the story of our universe. And as we uncover more about their impact, we move closer to understanding the grand narrative of cosmic evolution. Next, we'll dive into another intriguing connection: how gamma-ray bursts and fast radio bursts, two of the universe's most mysterious phenomena, might be linked. Now, let's turn our attention to another cosmic mystery that shares some striking similarities with gamma-ray bursts: fast radio bursts, or FRB. These fleeting bursts of radio waves last just milliseconds, but they pack an incredible amount of energy, much like their gamma-ray counterparts. While both phenomena are incredibly powerful and enigmatic, they also have key differences that make them unique. For instance, FRBs are detected in radio wavelengths, while GRBs are observed in gamma rays, the highest energy form of light. Despite these differences, scientists have begun to uncover intriguing connections between the two. One of the most compelling theories suggests that some FRBs may originate from Magnetars, highly magnetized neutron stars that are also linked to certain types of gamma-ray bursts. Magnetars are known for their intense magnetic fields, which can trigger violent outbursts of energy. In fact, some of the most energetic GRBs are thought to be produced by magnetars, and recent observations have shown that these same objects might also be responsible for some FRBs. For example, in 2020, astronomers detected an FRB coming from a magnetar within our own galaxy, providing the first direct evidence linking these two phenomena. This discovery has opened up new avenues for understanding how magnetars can produce such diverse and powerful bursts of energy. Another similarity between GRBs and FRBs lies in their potential origins. Just as long-duration GRBs are often associated with the collapse of massive stars, some FRBs are thought to arise from cataclysmic events like neutron star mergers or the collapse of highly magnetized stellar remnants. However, not all FRBs fit this mold. Some appear to repeat, emitting multiple bursts over time, while others are one-off events. This variability has led scientists to propose multiple origins for FRBs, ranging from magnetars to more exotic sources like black holes or even advanced extraterrestrial civilizations, though the latter remains highly speculative. Recent advancements in technology have allowed astronomers to study FRBs and GRBs in greater detail than ever before. Instruments like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have detected hundreds of FRBs, while gamma-ray observatories like Fermi and Swift continue to monitor the skies for GRBs. By comparing the properties of these bursts, researchers are piecing together a clearer picture of how they might be connected. For instance, both GRBs and FRBs often leave behind afterglows, fainter emissions that linger after the initial burst. Studying these afterglows has revealed clues about the environments where these events occur, such as the presence of dense gas or magnetic fields. The connection between GRBs and FRBs is more than just a cosmic curiosity. It's a window into the extreme physics of the universe. By studying these bursts, scientists can probe the behavior of matter and energy under conditions that are impossible to recreate on Earth. Each new discovery brings us closer to understanding the forces that shape the cosmos, from the birth of stars to the collisions of neutron stars. And as we continue to unravel the mysteries of GRBs and FRBs, we may find that these two phenomena are more intertwined than we ever imagined. Next, we'll explore how gamma-ray bursts are helping scientists test one of the most fundamental theories in physics, Einstein's theory of relativity. Now, let's shift our focus to how gamma-ray bursts are helping scientists put one of the most fundamental theories in physics to the test, Einstein's theory of relativity. GRB, with their extreme energy and distant origins, offer a unique cosmic laboratory for exploring the behavior of light, gravity, and time itself. One of the key predictions of relativity is that the speed of light in a vacuum is constant, a cornerstone of modern physics. But could this speed change under certain conditions? GRBs provide a way to investigate this question. When a gamma-ray burst occurs, its light travels across billions of light years to reach us. Along the way, it interacts with the fabric of space-time, which is shaped by gravity and the expansion of the universe. By analyzing the arrival times of different wavelengths of light from a GRB, scientists can test whether high-energy gamma rays and lower-energy photons, like X-rays or visible light, travel at the same speed. Any difference in their arrival times could hint at a breakdown in our understanding of relativity or even reveal new physics such as quantum gravity effects. One of the most fascinating aspects of GRBs is their ability to probe the effects of gravity on time. According to Einstein's theory, massive objects like black holes or neutron stars warp spacetime, causing time to slow down in their presence, a phenomenon known as gravitational time dilation. GRB, often originating near these extreme objects, allows scientists to observe this effect in action. For example, the afterglow of a GRB can show subtle changes in the timing of its emissions, providing evidence of how gravity influences the flow of time. Recent experiments have taken this even further. In 2017, the detection of gravitational waves from a neutron star merger, accompanied by a gamma-ray burst, offered a groundbreaking opportunity to test relativity. By comparing the arrival times of the gravitational waves and the gamma rays, researchers confirmed that both traveled at the same speed as predicted by Einstein. This not only validated a key aspect of relativity, but also demonstrated how GRBs can serve as cosmic tools for probing the limits of our understanding. The study of GRBs and relativity is far from over. As telescopes and detectors become more advanced, scientists hope to uncover even more subtle effects that could challenge or refine our current theories. For instance, some researchers are investigating whether GRBs could reveal evidence of extra dimensions or deviations from the laws of physics as we know them. Each new observation brings us closer to answering some of the deepest questions about the nature of space, time, and the universe itself. With this in mind, let's move on to another intriguing aspect of gamma-ray bursts, their mysterious ultra-long counterparts, which defy our expectations and challenge our understanding of these cosmic explosions. Now, let's turn our attention to one of the most puzzling types of gamma-ray bursts, the ultra-long GRBs. Unlike their shorter counterparts, which typically last from a few milliseconds to a couple of minutes, ultra-long GRBs can persist for several hours or even days. These extraordinary events challenge our understanding of how gamma-ray bursts work and what causes them in the first place. One leading theory suggests that ultra-long GRBs might be linked to the collapse of supergiant stars, some of the most massive stars in the universe. When a supergiant star exhausts its fuel, it doesn't just collapse into a neutron star or black hole in a matter of seconds. Instead, its immense size means the collapse can take much longer, potentially powering a gamma-ray burst that lasts for hours. This extended process could explain why ultra-long GRBs shine for so long, releasing energy over an unusually prolonged period. Another possibility is that the jets produced during a GRB interact with the surrounding material in a unique way. In some cases, these jets might plow through a thick cocoon of gas and dust left behind by the dying star. This interaction could slow down the jets and stretch out the burst's duration, creating the ultra-long phenomenon we observe. Alternatively, the jets might be powered by a long-lived central engine, such as a rapidly spinning black hole or magnetar, which continues to feed energy into the burst over an extended period. Studying ultra-long GRBs is no easy task. Their rarity makes them difficult to detect, and their prolonged emissions require telescopes to monitor them for much longer than typical GRBs. Additionally, their unusual behavior often defies the standard models used to explain shorter bursts, forcing scientists to rethink their assumptions about how these cosmic explosions work. For instance, the afterglows of ultra-long GRBs sometimes show unexpected patterns, suggesting that the mechanisms driving them might be more complex than previously thought. The implications of ultra-long GRBs go beyond just understanding these rare events. They could provide new insights into the life cycles of the most massive stars, the behavior of jets in extreme environments, and even the nature of the central engines that power GRBs. By studying these mysterious bursts, scientists hope to uncover clues that could help refine our models of gamma-ray bursts as a whole, shedding light on one of the universe's most energetic phenomena. With this in mind, let's explore another fascinating aspect of gamma-ray bursts their potential impact on the search for extraterrestrial life and the concept of habitable zones in the cosmos. Now, let's shift our focus to a thought-provoking question. Could gamma-ray bursts pose a threat to life elsewhere in the universe? The idea that GRBs might sterilize planets and hinder the development of life is both fascinating and unsettling. These cosmic explosions release such immense amounts of energy that, if one were to occur too close to a planet, it could have catastrophic effects. The intense gamma-ray radiation could strip away a planet's ozone layer, exposing its surface to harmful ultraviolet radiation from its host star. This would make it nearly impossible for life as we know it to survive, let alone thrive. Scientists have even proposed the concept of a GRB habitable zone, which refers to regions in galaxies where the likelihood of a GRB occurring is low enough to allow life to develop. In galaxies with frequent star formation, such as spiral galaxies, GRBs are more common, making these areas less hospitable for life. On the other hand, elliptical galaxies, which have lower rates of star formation, might offer safer environments for life to emerge and evolve. This raises intriguing questions about where we should focus our search for extraterrestrial life. Should we prioritize quieter regions of the universe? Or are there ways life could adapt to survive even in the presence of GRBs? Interestingly, Earth itself has likely experienced the effects of a nearby GRB in the past. Some researchers believe that a GRB occurring within a few thousand light-years of our planet could have contributed to mass extinctions, such as the Ordovician-Silurian event around 440 million years ago. While this theory is still debated, it highlights the potential impact GRBs could have on life, even on a planet as resilient as Earth. The implications of GRBs for the search for extraterrestrial life are profound. If GRBs are as destructive as we suspect, they could significantly narrow down the regions of the universe where life might exist. This adds another layer of complexity to the already challenging task of finding life beyond Earth. It also underscores the importance of understanding GRBs not just as cosmic curiosities, but as potential game changers in the story of life in the universe. With this in mind, let's turn our attention to another intriguing connection: how gamma-ray bursts might be linked to high-energy cosmic rays, and what this could tell us about the universe's most energetic processes. Now, let's explore another fascinating aspect of gamma-ray bursts: their potential connection to high-energy cosmic rays. Cosmic rays are particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They are some of the most energetic particles in the universe, and their origins have long puzzled scientists. Could GRBs be one of the sources of these mysterious cosmic rays? The answer might lie in the extreme environments created by these powerful explosions. When a gamma-ray burst occurs, it doesn't just release gamma rays, it also generates intense magnetic fields and accelerates particles to incredible speeds. Some researchers believe that these conditions could produce cosmic rays, which then travel across vast distances in space. In fact, there's evidence to support this idea. For example, in 2017, scientists detected a high-energy neutrino, a type of cosmic ray that appeared to originate from a gamma-ray burst. This discovery was a major breakthrough as it provided a direct link between GRBs and cosmic rays. However, the connection isn't straightforward. While some cosmic rays may come from GRBs, others likely originate from different sources, such as supernova remnants or active galactic nuclei. The challenge lies in pinpointing exactly which cosmic rays are linked to GRBs and which are not. This requires precise observations and advanced detection methods, such as neutrino telescopes and cosmic ray observatories. By studying these particles, scientists hope to unravel the mysteries of both GRBs and cosmic rays, shedding light on the universe's most energetic processes. The implications of this research are profound. If GRBs are indeed a significant source of cosmic rays, it would deepen our understanding of how these bursts shape the cosmos. It could also help us piece together the broader picture of how energy and matter are distributed throughout the universe. Moreover, studying cosmic rays from GRBs might provide clues about the environments in which these bursts occur, such as the magnetic fields and particle densities in their vicinity. As we continue to explore this connection, one thing is clear: gamma-ray bursts are not just isolated events, they are part of a larger cosmic puzzle. By studying their relationship with cosmic rays, we gain valuable insights into the forces that drive the universe's most extreme phenomena. And with that, let's turn our attention to another intriguing question. How do gamma-ray bursts help us study the elusive nature of dark energy? Now, shifting our focus to another layer of this cosmic mystery, let's dive deeper into the connection between gamma-ray bursts and high-energy cosmic rays. These cosmic rays, composed mostly of protons and atomic nuclei, zip through space at nearly the speed of light, carrying immense energy. But where do they come from? One compelling theory suggests that gamma-ray bursts might be one of their sources, and the evidence is starting to stack up. When a gamma-ray burst erupts, it doesn't just unleash a torrent of gamma rays. It also creates extreme environments where particles can be accelerated to astonishing speeds. These conditions, combined with the intense magnetic fields generated during the burst, could be the perfect recipe for producing cosmic rays. In fact, in 2017, scientists made a groundbreaking discovery. They detected a high-energy neutrino, a type of cosmic ray that seemed to originate from a gamma-ray burst. This was a significant moment as it provided the first direct evidence linking GRBs to cosmic rays. But the story doesn't end there. While this discovery was a major step forward, it also highlighted the complexity of the problem. Not all cosmic rays come from gamma-ray bursts. Other sources, like supernova remnants or the cores of active galaxies, also contribute to the cosmic ray population. The challenge lies in figuring out which cosmic rays are tied to GRBs and which are not. This requires incredibly precise observations and advanced tools, such as neutrino telescopes and cosmic ray observatories, which can track these particles back to their origins. The implications of this research are far-reaching. If gamma-ray bursts are indeed a significant source of cosmic rays, it would reshape our understanding of how these bursts influence the universe. It could also help us map out the distribution of energy and matter across the cosmos. Additionally, studying cosmic rays from GRBs might reveal more about the environments where these bursts occur, such as the strength of magnetic fields or the density of particles in their vicinity. As scientists continue to explore this connection, one thing is certain: gamma-ray bursts are more than just fleeting flashes of light. They are key players in the universe's most energetic processes. By unraveling their relationship with cosmic rays, we're not just solving a cosmic puzzle, we're gaining a deeper understanding of the forces that shape our universe. And with that, let's move on to another fascinating question. How do gamma-ray bursts help us probe the mysteries of dark energy? Now, turning our attention to another profound mystery of the cosmos, let's explore how gamma-ray bursts might hold the key to understanding dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the greatest puzzles in modern astrophysics. But here's where gamma-ray bursts come into play. They could serve as cosmic beacons, helping us measure distances across the universe and shed light on this enigmatic force. Gamma-ray bursts are incredibly bright, making them visible across vast cosmic distances. This brightness allows scientists to use them as standard candles, objects with known luminosity that can help calculate distances in space. By measuring the redshift of a GRB, how much its light has stretched as the universe expands, researchers can determine how far away it is. This information, combined with the burst's observed brightness, provides a way to map the expansion rate of the universe over time. But why is this important for studying dark energy? The expansion rate of the universe isn't constant, it's speeding up, and dark energy is believed to be the cause. By using GRBs to measure distances at different points in cosmic history, scientists can track how the expansion rate has changed. This data helps refine our understanding of dark energy's properties, such as its strength and how it behaves over time. However, using GRBs as standard candles isn't without challenges. Unlike supernova, which have more predictable brightness, GRBs vary widely in their energy output. This variability makes it harder to use them as precise distance markers. To overcome this, scientists have developed techniques to calibrate GRBs based on their afterglows and other observable features. These methods allow researchers to extract reliable distance measurements, even from the most energetic and unpredictable bursts. The potential of GRBs in dark energy research is immense. Because they can be detected at such great distances, they offer a way to probe the universe's expansion during its early stages, when dark energy's influence was just beginning to take hold. This could provide crucial insights into how dark energy has shaped the cosmos over billions of years. As we continue to study gamma-ray bursts, their role in unraveling the mysteries of dark energy becomes increasingly clear. These cosmic explosions are not just fleeting flashes of light, they are powerful tools that help us peer into the deepest corners of the universe and uncover the forces that govern its evolution. And with that, let's move on to another intriguing question. What can gamma-ray bursts tell us about the cosmic microwave background, the afterglow of the Big Bang? Now, let's take a closer look at how gamma-ray bursts are helping scientists measure distances in the universe and study its expansion rate. While GRBs are incredibly bright and visible across vast cosmic distances, using them as precise distance markers isn't straightforward. One of the biggest challenges is their variability. No two gamma-ray bursts are exactly alike. Some release an enormous amount of energy in just a few seconds, while others emit less energy but last much longer. This unpredictability makes it difficult to use GRBs as reliable, standard candles, objects with known brightness that help calculate distances. To tackle this issue, researchers have developed innovative techniques to calibrate GRBs. One approach involves studying their afterglows, the lingering emissions that follow the initial burst. By analyzing the afterglow's brightness and how it fades over time, scientists can estimate the burst's total energy output. Another method focuses on the relationship between the burst's peak energy and its overall luminosity. These correlations allow researchers to adjust their calculations, making GRBs more reliable as distance indicators. But why go through all this effort? The answer lies in the quest to understand dark energy, the mysterious force driving the universe's accelerated expansion. By using GRBs to measure distances at different points in cosmic history, scientists can track how the expansion rate has changed over billions of years. This data provides critical insights into dark energy's behavior, whether its strength has remained constant or varied over time. The implications of this research are profound. Gamma-ray bursts offer a unique window into the early universe, when dark energy's influence was just beginning to take hold. By studying these ancient bursts, scientists can piece together a timeline of the universe's expansion, shedding light on one of the greatest mysteries in modern astrophysics. And as our tools and techniques continue to improve, GRBs may hold even more secrets about the forces shaping our cosmos. With that in mind, let's shift our focus to another fascinating connection: how gamma-ray bursts can help us study the cosmic microwave background, the afterglow of the Big Bang. Now, let's turn our attention to a groundbreaking moment in astrophysics: the detection of GRB 170,817a. This gamma-ray burst holds a special place in history as the first ever observed alongside gravitational waves, ripples in spacetime predicted by Einstein over a century ago. The event marked a monumental leap in our understanding of the universe, as it confirmed a long-held theory that short gamma-ray bursts are produced by the collision of neutron stars. On August 17, 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger located about 130 million light-years away. Just 2 seconds later, NASA's Fermi Gamma-Ray Space Telescope spotted a short gamma-ray burst originating from the same region of the sky. This simultaneous detection was a game-changer. For the first time, scientists had both gravitational waves and electromagnetic signals, light, gamma rays, and more, to study a single cosmic event. This multi-messenger approach provided a wealth of data, offering unprecedented insights into the physics of neutron star mergers and the origins of short GRBs. The observations revealed that when two neutron stars collide, they not only produce a gamma-ray burst but also eject heavy elements like gold and platinum into space. This discovery solved a long-standing mystery about the origins of these precious metals, showing that neutron star mergers are cosmic forges for some of the universe's most valuable materials. Additionally, the event allowed scientists to test theories about the speed of gravity, confirming that it travels at the speed of light, just as Einstein predicted. GRB 170,817A wasn't just a scientific breakthrough, it was a testament to the power of collaboration across different fields of astronomy. By combining gravitational wave data with observations from telescopes across the electromagnetic spectrum, researchers pieced together a detailed picture of one of the most violent and energetic events in the cosmos. This event opened a new era of multi-messenger astronomy, where combining different types of signals allows us to explore the universe in ways never before possible. As we continue to unravel the mysteries of gamma-ray bursts, GRB 170,817A stands as a shining example of how far we've come and how much more there is to discover. Next, we'll explore how gamma-ray bursts can serve as cosmic time machines, offering glimpses into the early universe and the first stars that ever shone. Shifting our gaze even further back in time, gamma-ray bursts offer us a unique window into the early universe, acting as cosmic time machines that reveal the secrets of its infancy. These distant explosions, some occurring just a few 100 million years after the Big Bang, allow scientists to study the first stars and galaxies that ever formed. Known as Population 3 stars, these ancient celestial objects were massive, hot, and short-lived, ending their lives in spectacular supernova that likely triggered some of the earliest gamma-ray bursts. By studying the light from these bursts, researchers can piece together the conditions of the universe during its formative years, a period often referred to as the cosmic dawn. However, detecting and analyzing these ancient GRBs is no easy task. The light from these events has traveled for billions of years, stretched and dimmed by the expansion of the universe. This phenomenon, known as redshift, makes these bursts incredibly faint and difficult to observe. To overcome this challenge, astronomers rely on powerful telescopes like the James Webb Space Telescope and ground-based observatories equipped with advanced instruments. These tools allow scientists to capture the faint afterglows of GRBs and analyze their spectra, revealing clues about the chemical composition and density of the early universe. One of the most remarkable aspects of using GRBs to study the early universe is their ability to act as cosmic beacons. As their light passes through clouds of gas and dust, it leaves behind absorption lines in their spectra, much like fingerprints. These lines provide valuable information about the intergalactic medium and the first structures that formed in the universe. For example, the detection of heavy elements in the spectra of high redshift GRBs suggests that even the earliest stars were capable of forging these elements, challenging previous assumptions about the timeline of cosmic chemical evolution. The significance of GRBs in understanding the cosmic dawn cannot be overstated. They not only shed light on the formation of the first stars and galaxies, but also help us trace the evolution of the universe itself. By studying these ancient explosions, scientists can test theories about the reionization era, when the first stars and galaxies ionized the surrounding gas, transforming the universe from a dark, opaque state to the transparent cosmos we see today. This era, which occurred roughly 1 billion years after the Big Bang, remains one of the most mysterious chapters in cosmic history, and GRBs are one of our best tools for unraveling its secrets. As we continue to push the boundaries of our observational capabilities, gamma-ray bursts will undoubtedly play a crucial role in uncovering the story of the universe's beginnings. Next, we'll delve into the fascinating connection between GRBs and magnetars, highly magnetized neutron stars that may hold the key to some of the most energetic bursts in the cosmos. Now, let's turn our attention to one of the most intriguing theories in gamma-ray burst research: the connection between GRBs and magnetars. Magnetars are a special type of neutron star, but with a twist. They possess magnetic fields trillions of times stronger than Earth. These cosmic powerhouses are thought to be behind some of the most energetic bursts in the universe, including certain gamma-ray bursts. The idea is that when a magnetar undergoes a sudden release of energy, often due to a starquake or a rearrangement of its magnetic field, it can produce an intense burst of gamma rays. This theory gained traction when scientists observed X-ray flares accompanying some GRBs, which matched the expected behavior of magnetars. These flares, lasting from seconds to minutes, are thought to be the aftermath of the magnetar's violent activity, providing a kind of cosmic signature that links these neutron stars to GRBs. However, studying magnetars is no simple task. Their extreme magnetic fields and rapid spin rates make them some of the most unpredictable objects in the universe. Additionally, magnetars are relatively rare and their bursts are fleeting, making it difficult to catch them in the act. Despite these challenges, advancements in X-ray and gamma-ray telescopes have allowed researchers to gather more data, strengthening the case for magnetars as GRB progenitors. One of the most compelling pieces of evidence came from the detection of a magnetar flare in a galaxy far beyond our own, which bore striking similarities to the X-ray afterglows seen in some GRBs. This discovery not only supports the theory, but also opens up new questions about how magnetars form and evolve. Could they be the remnants of massive stars that collapsed in a way that amplified their magnetic fields? Or are they the result of rare cosmic events like the merger of neutron stars? As we continue to explore the mysteries of magnetars, their connection to gamma-ray bursts offers a fascinating glimpse into the extreme physics of the universe. These highly magnetized neutron stars remind us that even in the vastness of space, some of the most powerful forces are hidden within the smallest objects. Next, we'll explore how GRBs can shed light on the evolution of galaxies, tracing the story of star formation and cosmic history through their explosive light. Shifting our focus to the broader cosmic picture, gamma-ray bursts also serve as powerful tools for understanding the evolution of galaxies. These explosive events, often occurring in distant corners of the universe, leave behind afterglows that act like cosmic flashlights, illuminating the environments in which they occur. By studying these afterglows, scientists can trace the history of star formation and the enrichment of elements in galaxies across billions of years. When a GRB occurs, its afterglow interacts with the surrounding gas and dust, absorbing certain wavelengths of light. This absorption creates a unique fingerprint in the afterglow's spectrum, revealing the chemical composition of the host galaxy. Elements like carbon, oxygen, and iron, which are forged in the hearts of stars and scattered into space during supernova, leave distinct marks in the light. By analyzing these signatures, researchers can piece together how galaxies have evolved over time, from their earliest stages to the present day. One of the most fascinating aspects of this research is the ability to study galaxies that are otherwise too faint or distant to observe directly. GRBs act as natural probes, allowing astronomers to peer into the chemical makeup of galaxies that existed when the universe was just a fraction of its current age. For example, the detection of heavy elements in the afterglows of high redshift GRBs has provided evidence that even the earliest galaxies were already rich in metals, suggesting that star formation and supernova activity began much earlier than previously thought. This connection between GRBs and galactic evolution also sheds light on the life cycles of stars and the processes that shape galaxies. By tracing the distribution of elements across different galaxies, scientists can better understand how stars are born, live, and die, and how their remnants contribute to the cosmic ecosystem. GRB, in this sense, are not just fleeting flashes of light but also storytellers, revealing the intricate history of the universe's building blocks. As we continue to unravel the mysteries of gamma-ray bursts, their role in studying galactic evolution becomes increasingly clear. These cosmic explosions not only mark the end of massive stars but also provide a window into the past, helping us understand how galaxies grow, change, and shape the universe as we know it. Next, we'll dive into one of the brightest GRBs ever observed, a record-breaking event that captivated astronomers and offered new insights into the mechanics of these extraordinary phenomena. Now, let's turn our attention to one of the most extraordinary gamma-ray bursts ever recorded, GRB 080319b. This event, which took place in March 2008, holds the distinction of being one of the brightest GRBs in history, so luminous that it was briefly visible to the naked eye from Earth. Imagine looking up at the night sky and witnessing a flash of light brighter than most stars, originating from a cosmic explosion billions of light years away. That's exactly what happened with GRB 080319b, a phenomenon that left astronomers in awe and sparked intense scientific curiosity. The incredible brightness of this GRB is believed to be due to a rare alignment of its jet with Earth. Gamma-ray bursts emit their energy in narrow, highly focused jets, and when one of these jets points directly at us, the burst appears exceptionally bright. In the case of GRB 080319b, the jet was almost perfectly aligned with our line of sight, amplifying its observed brightness to unprecedented levels. This alignment allowed telescopes and even human eyes to detect the burst, making it a once-in-a-lifetime event for both scientists and amateur stargazers. But the significance of GRB 080319b goes beyond its sheer brightness. This event provided a unique opportunity to study the mechanics of gamma-ray bursts in greater detail. The burst's afterglow, which lasted for several days, was observed across multiple wavelengths, from gamma rays to visible light. These observations revealed critical insights into the structure and behavior of GRB jets, including how they accelerate particles to near light speeds and how their energy is distributed. The data from this burst also helped refine models of how GRBs form and evolve, shedding light on the processes that drive these cosmic explosions. One of the most intriguing implications of GRB 080319b is what it tells us about the rarity of such events. While gamma-ray bursts are already rare, those bright enough to be seen without telescopes are even more exceptional. This burst serves as a reminder of how much we still have to learn about the universe's most energetic phenomena, and how fortunate we are when nature provides us with such a clear and vivid example to study. As we continue to explore the mysteries of gamma-ray bursts, events like GRB 080319b stand out as milestones in our understanding. They challenge our assumptions, refine our theories, and remind us of the sheer power and beauty of the cosmos. Next, we'll delve into how gamma-ray bursts can be used to study the intergalactic medium, the vast and mysterious space between galaxies, and what these observations reveal about the large-scale structure of the universe. Shifting our focus to the vast spaces between galaxies, let's explore how gamma-ray bursts serve as cosmic flashlights, illuminating the intergalactic medium. This mysterious expanse, filled with diffuse gas and dust, is often too faint to study directly. but when a GRB occurs, its afterglow provides a brilliant beacon that cuts through the darkness, allowing scientists to analyze the gas that lies between galaxies. The key to this process lies in the absorption lines found in the spectra of GRB afterglows. As the light from a GRB travels through the intergalactic medium, it passes through clouds of gas. These clouds absorb specific wavelengths of light, leaving behind distinct fingerprints in the GRB spectrum. By studying these absorption lines, astronomers can determine the composition, density, and temperature of the gas, as well as its distribution across the universe. It's like using a cosmic prism to break apart the light and uncover the secrets hidden within. One of the most fascinating aspects of this research is what it reveals about the large-scale structure of the universe. The intergalactic medium isn't uniform, it's a complex web of filaments and voids, shaped by the gravitational pull of dark matter and the expansion of the universe. GRB, especially those at extreme distances, allow us to map this cosmic web in incredible detail. By tracing the absorption lines in their afterglows, scientists can piece together how matter is distributed across billions of light years, offering insights into the universe's evolution and the forces that govern its growth. The significance of this work extends beyond just understanding the intergalactic medium. It also helps us test theories about the early universe, such as how the first galaxies formed and how they influenced their surroundings. GRBs act as time capsules, preserving information about the conditions of the universe at different stages of its history. By studying these bursts, we're not just looking at the gas between galaxies, we're peering back in time, uncovering the story of how the cosmos came to be. As we continue to harness the power of GRBs to study the intergalactic medium, we gain a deeper appreciation for the interconnectedness of the universe. These bursts remind us that even the emptiest regions of space hold clues to the grandest mysteries of all. Next, we'll turn our attention to the intriguing connection between gamma-ray bursts and supermassive black holes, and how these colossal objects might be linked to some of the most powerful explosions in the cosmos. Now, let's turn our attention to one of the most intriguing theories in gamma-ray burst research: the connection between GRBs and supermassive black holes. These colossal objects lurking at the hearts of galaxies are thought to play a role in some of the most powerful explosions in the universe. But how exactly are these two phenomena linked? Let's dive in. Supermassive black holes, millions or even billions of times more massive than our Sun, are known for their immense gravitational pull and their ability to influence their surroundings. In some galaxies, these black holes are surrounded by swirling disks of gas and dust known as accretion disks. As material spirals into the black hole, it heats up and emits enormous amounts of energy, creating what we call active galactic nuclei, or AN. It's within these energetic environments that scientists believe some GRBs may originate. One piece of evidence supporting this theory is the detection of GRBs in or near active galactic nuclei. These bursts often exhibit unique characteristics, such as unusually long durations or complex light curves, which suggest they might be influenced by the extreme conditions near supermassive black holes. For example, the intense magnetic fields and relativistic jets associated with AGN could potentially trigger or amplify GRBs, creating some of the most energetic events we've ever observed. However, studying this connection is no easy task. The environments around supermassive black holes are chaotic and filled with high-energy radiation, making it difficult to isolate the specific mechanisms that might produce GRBs. Additionally, the vast distances involved mean that the light from these events often takes billions of years to reach us, complicating our ability to observe them in detail. Despite these challenges, advancements in telescope technology and multi-wavelength observations are helping scientists piece together this cosmic puzzle. The implications of this research are profound. If GRBs are indeed linked to supermassive black holes, it could provide new insights into the behavior of these enigmatic objects and the processes that drive their activity. It could also help us understand how black holes influence the evolution of their host galaxies, shaping the universe on the largest scales. As we continue to explore this connection, we're reminded once again of the intricate web of relationships that define our cosmos. Next, we'll shift our focus to another fascinating aspect of gamma-ray bursts, their role in helping us understand the properties of neutron stars, the dense remnants of massive stars that have gone supernova. Stay tuned as we uncover how these exotic objects are tied to some of the most powerful explosions in the universe. Now, let's venture into the fascinating world of neutron stars and uncover how gamma-ray bursts serve as cosmic tools to study these incredibly dense remnants of stellar explosions. Neutron stars, born from the violent deaths of massive stars, are among the most exotic objects in the universe. Packing the mass of a star into a sphere no larger than a city, they are so dense that a single teaspoon of neutron star material would weigh billions of tons. But how do gamma-ray bursts help us unlock the secrets of these extreme objects? Let's find out. One of the key ways GRBs provide insights into neutron stars is through their connection to short-duration bursts. Many short GRBs are believed to result from the collision or merger of two neutron stars. When these incredibly dense objects spiral into each other, they release a tremendous amount of energy in the form of gamma rays, gravitational waves, and other radiation. By studying the light and signals from these events, scientists can infer the properties of the neutron stars involved, such as their mass, size, and internal structure. For example, the detection of gravitational waves from neutron star mergers has allowed researchers to test theories about how matter behaves under such extreme conditions, providing clues about the nature of neutron star cores. Another way GRBs shed light on neutron stars is through their magnetic fields. Some neutron stars, known as Magnetars, possess magnetic fields trillions of times stronger than Earth. These intense fields can trigger powerful bursts of gamma rays, often observed as GRBs. By analyzing the energy and patterns of these bursts, scientists can study the behavior of magnetic fields in neutron stars and how they influence the star's surroundings. This research helps us understand not only the physics of neutron stars, but also the broader role of magnetic fields in shaping cosmic events. GRBs also offer a unique window into the evolution of neutron stars. Over time, neutron stars can cool, spin down, or even collapse into black holes. Observations of GRBs associated with neutron stars provide data on how these objects change over their lifetimes. For instance, the detection of X-ray flares or afterglows following a GRB can reveal information about the neutron star's rotation, temperature, and interactions with its environment. These findings help refine our models of neutron star evolution and their ultimate fates. The significance of GRBs in studying neutron stars cannot be overstated. These bursts act as cosmic laboratories, allowing us to probe conditions that are impossible to replicate on Earth. By combining GRB observations with data from gravitational wave detectors and other telescopes, scientists are piecing together a clearer picture of these enigmatic objects. As we continue to explore the connection between GRBs and neutron stars, we gain not only a deeper understanding of these stellar remnants, but also new insights into the fundamental laws of physics that govern our universe. Next, we'll turn our attention to one of the most energetic gamma-ray bursts ever recorded, GRB 130427A, and explore what makes it so extraordinary. Stay tuned as we uncover the mysteries behind this record-breaking cosmic explosion. Now, let's dive into the extraordinary story of GRB 130427A, one of the most powerful gamma-ray bursts ever recorded. Detected in April 2013, this event stunned astronomers with its sheer intensity, releasing more energy in just a few seconds than our Sun will emit over its entire 10 billion-year lifetime. But what made this GRB so exceptionally energetic? The answer lies in the unique conditions surrounding its origin. One leading theory suggests that GRB 130427 was powered by a highly magnetized jet, a narrow beam of particles and radiation traveling at nearly the speed of light. These jets are thought to form when a massive star collapses into a black hole, launching a focused stream of energy into space. In the case of GRB 130427a, the jet's magnetic field may have been unusually strong, amplifying the burst's energy output to unprecedented levels. This magnetic boost could explain why the GRB was so bright and why its afterglow remained visible for weeks, allowing scientists to study it in remarkable detail. Another fascinating aspect of this event is its distance. GRB 130427 occurred approximately 3.6 billion light-years away, making it one of the closest long-duration GRBs ever observed. Its relative proximity provided astronomers with a rare opportunity to study the burst's properties with exceptional clarity. Observations revealed that the jet was not only highly magnetized but also remarkably stable, maintaining its structure over vast distances. This stability challenges existing models of GRB jets, suggesting that our understanding of these cosmic phenomena may need to be revised. The implications of GRB 130427 extend far beyond its record-breaking energy. By studying this event, scientists gained valuable insights into the physics of relativistic jets, the behavior of magnetic fields in extreme environments, and the mechanisms that power gamma-ray bursts. These findings have helped refine theoretical models, bringing us closer to understanding how such colossal amounts of energy can be generated and focused in such a short time. As we continue to unravel the mysteries of GRB 130427a, we are reminded of the incredible power and complexity of the universe. This extraordinary event not only pushes the boundaries of our knowledge, but also highlights the importance of studying gamma-ray bursts as windows into the most extreme processes in the cosmos. Next, we'll explore how GRBs can help us study the properties of cosmic dust, shedding light on the building blocks of galaxies and the universe itself. Stay tuned as we uncover more secrets hidden in the light of these distant explosions. Now, let's shift our focus to a different but equally fascinating aspect of gamma-ray bursts, their role in helping us study cosmic dust. While GRBs are known for their explosive power, their afterglows serve as powerful tools for probing the dusty environments of distant galaxies. When a GRB occurs, its intense light travels through space, interacting with cosmic dust along the way. This interaction leaves behind a unique fingerprint in the GRB's afterglow, providing scientists with valuable clues about the dust's properties. One of the key ways astronomers study cosmic dust is by analyzing the GRB's spectrum, the breakdown of its light into different wavelengths. As the light passes through dust, certain wavelengths are absorbed or scattered, a phenomenon known as extinction. By measuring how much light is lost at specific wavelengths, scientists can determine the amount and composition of dust in the galaxy hosting the GRB. This information is crucial because cosmic dust plays a vital role in galaxy evolution, influencing star formation and the chemical enrichment of the universe. What makes GRBs particularly useful for this kind of study is their brightness and distance. Because GRBs are so luminous, their afterglows can be observed even in galaxies billions of light-years away. This allows astronomers to study cosmic dust in some of the earliest galaxies in the universe, offering a glimpse into the conditions that existed when galaxies were still young. For example, observations of GRB afterglows have revealed that the dust in early galaxies was often different from the dust we see in more recent galaxies, suggesting that the processes creating dust evolved over time. The study of cosmic dust through GRBs also has broader implications for our understanding of the universe. Dust is not just a passive component of galaxies. It actively shapes their evolution by cooling gas, shielding young stars from harmful radiation, and providing the raw materials for planet formation. By using GRBs as cosmic probes, scientists can piece together how dust influences these processes across different stages of a galaxy's life. As we continue to explore the connection between GRBs and cosmic dust, we gain deeper insights into the building blocks of galaxies and the universe itself. These distant explosions not only illuminate the most extreme events in the cosmos, but also shed light on the subtle, yet crucial, role of dust in shaping the universe we see today. Next, we'll delve into how GRBs are linked to regions of intense star formation, uncovering the relationship between these explosive events and the birth of new stars. Stay with us as we journey further into the mysteries of the cosmos. Now, let's turn our attention to another intriguing connection in the cosmos, the link between gamma-ray bursts and star formation. GRBs are not just random cosmic explosions. They often occur in regions where stars are being born at an extraordinary rate. These areas, known as starburst galaxies, are like cosmic nurseries, teeming with young, massive stars and the raw materials needed to create them. But what does this tell us about the origins of GRBs and their role in the universe? One of the key pieces of evidence supporting this connection is the observation that many long-duration GRBs are found in starburst galaxies. These galaxies are characterized by their intense star-forming activity, producing stars at rates hundreds or even thousands of times faster than our own Milky Way. The presence of GRBs in these environments suggests that the same processes driving star formation may also trigger these powerful explosions. For example, when a massive star collapses at the end of its life, it can produce a GRB, and such stars are more likely to form in regions where star formation is already rampant. But why does this matter? Understanding the relationship between GRBs and star formation helps us piece together the life cycle of stars and galaxies. GRBs act as cosmic signposts, pointing us toward regions where the universe is actively creating new stars. By studying these bursts, astronomers can map out the locations and conditions of star formation across the cosmos, even in galaxies billions of light years away. This provides a unique window into how galaxies evolve over time and how the birth of stars shapes the universe. Moreover, the connection between GRBs and star formation has broader implications for our understanding of the early universe. In the distant past, galaxies were much more active in forming stars than they are today. By detecting GRBs in these ancient galaxies, scientists can study the conditions that existed during the universe's youth when star formation was at its peak. This allows us to trace the history of star formation and understand how it has changed over billions of years. As we continue to explore this fascinating link, we uncover more about the intricate dance between the birth of stars and the explosive events that mark their deaths. GRBs not only illuminate the most dramatic moments in the cosmos, but also help us understand the processes that drive the creation of stars and galaxies. Next, we'll dive into how GRBs have revolutionized the field of gamma-ray astronomy, shedding light on some of the most energetic phenomena in the universe. Stay tuned as we uncover more secrets of these cosmic powerhouses. Now, let's shift our focus to how gamma-ray bursts have transformed the field of gamma-ray astronomy. These cosmic explosions have become a cornerstone of high-energy astrophysics, offering scientists an unprecedented look into some of the most extreme processes in the universe. By studying GRBs, researchers have gained valuable insights into the behavior of matter and energy under conditions that are impossible to replicate on Earth. The development of specialized gamma-ray telescopes has been crucial in this revolution. Instruments like the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory have been designed to detect and analyze the fleeting bursts of gamma rays emitted by GRBs. These telescopes are equipped with sensitive detectors that can capture the initial flash of a GRB, as well as its afterglow, across multiple wavelengths. This capability has allowed astronomers to piece together the sequence of events that occur during a GRB, from the initial explosion to the fading remnants. One of the most significant contributions of GRBs to gamma-ray astronomy is their role in probing the high-energy universe. GRBs produce some of the most energetic photons ever observed, with energies reaching billions of times that of visible light. By studying these photons, scientists can investigate phenomena such as particle acceleration, magnetic field dynamics, and the behavior of matter at near light speeds. GRBs have also provided a unique opportunity to test theories of physics under extreme conditions, including the nature of space-time and the limits of Einstein's theory of relativity. Moreover, GRBs have helped astronomers map the distribution of gamma-ray sources across the universe. Because GRBs are so bright, they can be detected from vast distances, allowing scientists to study the gamma-ray sky on a cosmic scale. This has led to the discovery of new classes of gamma-ray emitters, such as blazars and pulsars, and has deepened our understanding of the processes that produce high-energy radiation. The impact of GRBs on gamma-ray astronomy extends beyond scientific discovery. These events have also driven technological advancements, pushing the development of more sensitive and versatile telescopes. As a result, the field of gamma-ray astronomy has grown rapidly, with new missions and instruments being planned to further explore the high-energy universe. In essence, GRBs have opened a new window into the cosmos, revealing a universe that is far more dynamic and energetic than we once imagined. By continuing to study these extraordinary events, scientists are not only unraveling the mysteries of GRBs, but also gaining a deeper understanding of the fundamental forces that shape our universe. Next, we'll explore the intriguing mystery of GRB 060614, a long-duration burst that defied expectations and challenged our understanding of these cosmic phenomena. Stay tuned as we uncover more about this enigmatic event. Now, let's turn our attention to one of the most puzzling gamma-ray bursts ever observed, GRB 060614. This long-duration burst, detected in 2006, stood out from the crowd for one striking reason: it didn't have an accompanying supernova. This was a major surprise, as long GRBs are typically linked to the explosive deaths of massive stars, which leave behind a supernova as a signature. So, what made GRB 060614 so different? One leading theory suggests that this burst might have been the result of a failed supernova. In this scenario, a massive star collapses under its own gravity, but instead of producing a bright supernova, it forms a black hole directly, releasing a gamma-ray burst without the usual fireworks. Another possibility is that GRB 060614 had a completely different origin, such as the merger of two compact objects like neutron stars or black holes. While these events are usually associated with short GRBs, some scientists believe they could also produce longer bursts under certain conditions. The mystery of GRB 060614 has significant implications for how we classify gamma-ray bursts. Traditionally, GRBs are divided into two categories, long and short, based on their duration and presumed origins. However, this event challenges that binary classification, suggesting that the universe might produce GRBs in ways we don't yet fully understand. It raises questions about whether there are additional subcategories or entirely new types of GRBs waiting to be discovered. This anomaly also highlights the importance of continued observation and analysis. By studying bursts like GRB 060614, scientists can refine their models and better understand the diverse mechanisms that produce these cosmic explosions. It's a reminder that the universe often defies our expectations, pushing us to rethink our assumptions and explore new possibilities. As we move forward, the mystery of GRB 060614 serves as a fascinating case study in the ever-evolving field of gamma-ray astronomy. Next, we'll dive into the role of GRBs in studying relativistic jets, another area where these cosmic events are shedding light on some of the most extreme physics in the universe. Stay tuned as we explore how GRBs are helping us unravel the secrets of these high-speed phenomena. Now, let's shift our focus to another fascinating aspect of gamma-ray bursts, their role in helping us understand relativistic jets. These jets are some of the most extreme phenomena in the universe, and GRBs provide a unique laboratory for studying them. But what exactly are relativistic jets, and why are they so important? Relativistic jets are narrow beams of particles and radiation that shoot out from certain cosmic objects at nearly the speed of light. They're not just found in GRBs, they're also observed in other high-energy systems like quasars and active galactic nuclei. However, GRB jets are particularly special because they're incredibly powerful and short-lived, making them ideal for studying the physics of these high-speed outflows. One key difference between GRB jets and those in other systems is their energy. GRB jets are among the most energetic in the universe, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. This makes them a perfect natural laboratory for testing theories about how jets are formed and how they behave under extreme conditions. For example, scientists can study how magnetic fields and particle acceleration work in these jets, which can help us understand similar processes in other cosmic objects. Another important aspect of GRB jets is their structure. Unlike the more diffuse jets seen in quasars, GRB jets are highly collimated, meaning they're tightly focused and travel in a straight line. This allows researchers to study the effects of relativistic speeds and the interaction between the jets and their surrounding environment in great detail. By analyzing the afterglows of GRBs, scientists can trace the evolution of these jets and learn how they shape the regions of space they pass through. The study of GRB jets also has broader implications for astrophysics. For instance, understanding how these jets form and propagate can shed light on the behavior of black holes and neutron stars, which are often the sources of these powerful outflows. Additionally, the insights gained from GRB jets can help us better understand other relativistic phenomena, such as the jets produced by supermassive black holes at the centers of galaxies. In many ways, GRBs are like cosmic flashlights, illuminating the physics of relativistic jets in ways that would otherwise be impossible. By studying these bursts, scientists are not only unraveling the mysteries of GRBs themselves, but also gaining a deeper understanding of the universe's most extreme environments. As we continue to explore these high-speed jets, we're reminded once again of the incredible power and complexity of the cosmos. Next, we'll take a closer look at how GRBs are helping us probe the cosmic microwave background, the faint afterglow of the Big Bang. Stay tuned as we uncover how these bursts are providing new insights into the earliest moments of our universe. Now, let's turn our attention to an extraordinary connection between gamma-ray bursts and one of the most important relics of the early universe, the cosmic microwave background, or CMB. This faint glow, often called the afterglow of the Big Bang, is a snapshot of the universe when it was just 380,000 years old. But how do GRBs, which occur billions of years later, help us study this ancient light? The answer lies in the way GRBs interact with the CMB. When the light from a gamma-ray burst travels across the universe, it passes through the cosmic microwave background. As it does, the CMB leaves subtle imprints on the GRB spectrum, like fingerprints on a window. By analyzing these imprints, scientists can measure the temperature and properties of the CMB at different points in cosmic history. This is especially useful because GRBs occur at such vast distances, allowing us to probe the CMB in regions of the universe that are otherwise difficult to observe. One of the most fascinating aspects of this connection is how GRBs can help us test the uniformity of the CMB. The cosmic microwave background is remarkably consistent across the sky, but tiny variations in its temperature tell us about the early universe's structure. GRBs act as cosmic probes, allowing us to measure these variations with incredible precision. For example, by studying the spectra of distant GRBs, researchers have confirmed that the CMB's temperature has remained remarkably stable over billions of years, just as predicted by the Big Bang theory. But the significance of GRBs goes even further. They also provide a unique way to study the epoch of recombination, the moment when the first atoms formed and the universe became transparent to light. During this period, the CMB was emitted, and GRBs help us understand how the universe transitioned from a hot, dense plasma to the cooler, more structured cosmos we see today. By analyzing the absorption lines in GRB spectra, scientists can trace the evolution of the early universe and test theories about how it expanded and cooled. Perhaps most importantly, GRBs offer a way to study the CMB in 3 dimensions. While traditional observations of the CMB give us a 2-dimensional map of the early universe, GRBs allow us to see how the CMB changes over time and distance. This 3-dimensional view provides new insights into the universe's expansion and the distribution of matter in its infancy. It's like having a time machine that lets us peer deeper into the past than ever before. In many ways, GRBs are like cosmic messengers carrying information about the universe's earliest moments. By studying their interaction with the CMB, we're not only learning more about gamma-ray bursts themselves, but also uncovering new details about the Big Bang and the birth of the cosmos. As we continue to explore this connection, we're reminded of how interconnected the universe truly is, from its most violent explosions to its faintest whispers of light. Next, we'll dive into the mysterious world of ultra-long gamma-ray bursts, events that defy our expectations and challenge our understanding of these cosmic phenomena. Stay with us as we uncover what makes these rare bursts so unique and what they can teach us about the universe's most extreme environments. Now, let's shift our focus to an exciting frontier where gamma-ray bursts are helping us push the boundaries of high-energy physics. These cosmic explosions are not just spectacular events in the universe. They also serve as natural laboratories for testing some of the most profound theories in physics, including quantum gravity and particle acceleration. Gamma-ray bursts are among the most energetic phenomena in the cosmos, releasing more energy in a few seconds than our Sun will emit over its entire lifetime. This incredible energy output makes them ideal for studying extreme physical processes that we can't replicate on Earth. For instance, GRBs allow scientists to probe the behavior of matter and energy under conditions of extreme density and temperature, similar to those that existed just moments after the Big Bang. One of the key areas where GRBs are making an impact is in the study of quantum gravity. This field seeks to unify Einstein's theory of general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the behavior of particles at the smallest scales. GRBs provide a unique opportunity to test predictions of quantum gravity theories, such as the idea that the speed of light might vary at extremely high energies. By analyzing the arrival times of gamma rays from distant bursts, researchers can look for tiny deviations that might hint at the quantum nature of spacetime. Another fascinating aspect of GRBs is their role in understanding particle acceleration. The jets produced during a GRB are thought to accelerate particles to nearly the speed of light, creating some of the most energetic cosmic rays ever observed. Studying these particles helps scientists refine models of how such extreme acceleration occurs, shedding light on processes that power not only GRBs but also other high-energy phenomena like supermassive black holes and quasars. However, using GRBs to study high-energy physics comes with its own set of challenges. One major hurdle is the sheer distance of these bursts, which makes it difficult to capture detailed data. Additionally, the brief duration of GRBs means that observations must be made quickly and precisely. To overcome these obstacles, scientists rely on a network of satellites and ground-based telescopes that work together to detect and analyze GRBs in real time. Instruments like the Fermi Gamma Ray Space Telescope and the Swift Observatory are crucial for capturing the fleeting signals of these cosmic explosions. The significance of GRBs in advancing our understanding of fundamental physics cannot be overstated. They provide a window into the most extreme environments in the universe, offering clues about the nature of space-time, the behavior of matter at its limits, and the origins of cosmic rays. As we continue to study these extraordinary events, we're not only unraveling the mysteries of gamma-ray bursts, but also gaining deeper insights into the laws that govern the cosmos. Next, we'll explore the intriguing mystery of GRB 050509b, the first short gamma-ray burst with a confirmed host galaxy, and what it revealed about the origins of these enigmatic events. Stay tuned as we uncover how this discovery reshaped our understanding of the universe's most fleeting cosmic explosions. Now, let's turn our attention to a groundbreaking discovery that changed the way we think about short gamma-ray bursts, GRB 050509b. This event marked a major milestone in astrophysics as it was the first short GRB ever to have its host galaxy identified. Before this discovery, the origins of short GRBs were shrouded in mystery, with scientists speculating about their causes but lacking concrete evidence. GRB 050509b provided the first clear link between short GRBs and neutron star mergers, offering a crucial piece of the puzzle in understanding these fleeting cosmic explosions. The significance of this discovery cannot be overstated. By pinpointing the host galaxy of GRB 050509b, researchers were able to confirm that short GRBs are not random events but are instead tied to specific astrophysical processes. The host galaxy, an elliptical galaxy located about 2 billion light-years away, provided vital clues about the environment in which the burst occurred. Elliptical galaxies are typically older and have lower rates of star formation, which aligned with the theory that short GRBs originate from the mergers of neutron stars, remnants of massive stars that have long since burned out. This discovery also had profound implications for our understanding of neutron star mergers. When two neutron stars collide, they release an enormous amount of energy in the form of gravitational waves, gamma rays, and other electromagnetic radiation. GRB 050509b provided the first observational evidence supporting this theory, paving the way for future discoveries like the historic detection of gravitational waves from a neutron star merger in 2017. By linking short GRBs to neutron star mergers, scientists gained a new tool for studying these cataclysmic events and their role in the universe. The implications of GRB 050509b extend beyond just understanding short GRBs. This discovery also shed light on the production of heavy elements in the universe. Neutron star mergers are believed to be a primary source of elements like gold and platinum, which are formed through a process called rapid neutron capture. By studying short GRBs, scientists can learn more about how these precious elements are created and distributed throughout the cosmos. However, the mystery of GRB 050509b also raised new questions. For instance, why did this particular burst produce such a faint afterglow compared to other short GRBs? Some researchers speculate that the angle of the jet relative to Earth or the properties of the surrounding environment might have played a role. These lingering questions highlight the complexity of GRBs and the need for continued observation and analysis. As we continue to explore the universe's most distant gamma-ray bursts, discoveries like GRB 050509b remind us of the power of observation and the importance of connecting the dots between theory and evidence. This event not only deepened our understanding of short GRBs, but also opened new avenues for exploring the cosmos. Next, we'll delve into how gamma-ray bursts are helping us study the properties of galaxy clusters, revealing even more about the large-scale structure of the universe. Stay tuned as we uncover the next chapter in this cosmic journey. Now, let's shift our focus to how gamma-ray bursts are helping us unlock the secrets of galaxy clusters, some of the largest structures in the universe. These massive collections of galaxies, bound together by gravity, are filled with hot gas, dark matter, and countless mysteries. GRB, with their incredibly bright afterglows, serve as powerful tools for studying these cosmic giants in ways that were once unimaginable. When a gamma-ray burst occurs, its afterglow can act like a cosmic flashlight, illuminating the gas and dust in the galaxy clusters it passes through. By analyzing the light from these afterglows, scientists can measure the properties of the intracluster medium, the hot gas that fills the space between galaxies in a cluster. This gas, which can reach temperatures of millions of degrees, plays a crucial role in the evolution of galaxy clusters, and GRBs provide a unique way to study its density, temperature, and chemical composition. One of the most fascinating aspects of using GRBs to study galaxy clusters is their ability to reveal the distribution of dark matter. Dark matter, which makes up about 85% of the universe's total matter, doesn't emit light, making it incredibly difficult to detect directly. However, its presence can be inferred through its gravitational effects on light. When the afterglow of a GRB passes through a galaxy cluster, the light can be bent and distorted by the cluster's gravitational field, a phenomenon known as gravitational lensing. By studying these distortions, scientists can map the distribution of dark matter within the cluster, shedding light on one of the universe's greatest mysteries. GRBs also provide insights into the large-scale structure of the universe. Galaxy clusters are not randomly scattered but are connected by vast filaments of gas and dark matter, forming a cosmic web. By observing how GRB afterglows interact with these structures, researchers can trace the intricate network of matter that defines the universe's architecture. This helps us understand how galaxy clusters form, evolve, and interact over billions of years. The significance of GRBs in studying galaxy clusters goes beyond just mapping their properties. These bursts also help us understand the role of galaxy clusters in the broader context of cosmic evolution. For example, the intracluster medium is a reservoir of heavy elements produced by supernova and neutron star mergers. By studying the chemical fingerprints in GRB afterglows, scientists can learn how these elements are distributed and recycled throughout the universe, contributing to the formation of new stars and planets. As we continue to explore the universe's most distant gamma-ray bursts, their role in studying galaxy clusters reminds us of the interconnectedness of cosmic phenomena. These bursts not only illuminate the hidden structures of the universe, but also deepen our understanding of how everything from the smallest particles to the largest galaxy clusters fits together in the grand tapestry of the cosmos. Next, we'll uncover how GRBs are helping us peer into the era of the first stars, offering a glimpse into the universe's earliest moments. Stay with us as we journey further into the mysteries of space. Now, let's turn our attention to one of the most intriguing possibilities in the study of gamma-ray bursts: their connection to the very first stars in the universe. These stars, known as population 3 stars, are thought to have formed just a few 100 million years after the Big Bang, during a time often referred to as the era of first light. Unlike the stars we see today, population 3 stars were composed almost entirely of hydrogen and helium, the simplest elements in the universe. They were massive, hot, and short-lived, and their explosive deaths may have played a key role in shaping the cosmos as we know it. Gamma-ray bursts offer a unique window into this ancient era. Because GRBs are so incredibly bright, they can be detected across vast cosmic distances, even from the earliest epochs of the universe. Some of the most distant GRBs ever observed have redshift so high that they provide a glimpse into a time when the first stars were just beginning to ignite. These high redshift GRBs are like cosmic time capsules, carrying information about the conditions and processes that existed during the universe's infancy. One of the strongest pieces of evidence linking GRBs to population 3 stars comes from their energy signatures. The explosions that produce GRBs are thought to be triggered by the collapse of massive stars, and population 3 stars with their enormous sizes would have been prime candidates for such cataclysmic events. When these stars exhausted their fuel and collapsed, they could have unleashed gamma-ray bursts that outshone entire galaxies, leaving behind a telltale afterglow that we can still detect billions of years later. Studying these ancient GRBs helps scientists piece together the story of how the first stars formed and evolved. For example, the light from GRB afterglows can reveal the chemical composition of the gas surrounding these early stars. This gas, enriched by the first supernova, would have contained the seeds of heavier elements like carbon, oxygen, and iron elements that are essential for the formation of planets and life as we know it. By analyzing these afterglows, researchers can trace the origins of the elements that make up our world today. The significance of GRBs in understanding the era of first light goes beyond just star formation. These bursts also provide clues about the reionization of the universe, a pivotal period when the first stars and galaxies ionized the surrounding hydrogen gas, transforming the cosmos from a dark, opaque state to the transparent universe we see today. GRBs that occurred during this time can help scientists map the progress of reionization and understand how the first structures in the universe influenced its evolution. As we continue to explore the universe's most distant gamma-ray bursts, their connection to the first stars reminds us of the profound interconnectedness of cosmic history. These bursts not only illuminate the birth of the first stars, but also help us understand how the universe itself grew from a simple, primordial state into the complex and beautiful tapestry we observe today. Next, we'll delve into how GRBs are helping us study the remnants of supernova, shedding light on the explosive deaths of massive stars. Stay with us as we uncover more secrets of the cosmos. Now, shifting our focus to the aftermath of these cosmic explosions, let's explore how gamma-ray bursts are helping us unravel the mysteries of supernova remnants. When a massive star reaches the end of its life and explodes as a supernova, it leaves behind a rapidly expanding cloud of gas and dust known as a supernova remnant. These remnants are not just debris, they are dynamic laboratories that reveal the final moments of a star's life and the processes that shape the interstellar medium. Gamma-ray bursts, particularly those associated with supernova, provide a unique opportunity to study these remnants in detail. When a GRB occurs, the intense burst of energy can illuminate the surrounding environment, including any nearby supernova remnants. This illumination allows scientists to observe how the remnants interact with their surroundings, such as the shock waves they generate and the way they enrich the interstellar medium with heavy elements. One of the key insights GRBs offer is into the chemical composition of supernova remnants. As the remnants expand, they carry with them the elements forged in the heart of the dying star, such as iron, nickel, and silicon. By analyzing the light from GRB afterglows, researchers can detect these elements and measure their abundance. This information helps us understand how supernova contribute to the chemical evolution of galaxies, seeding the universe with the building blocks of planets and life. GRBs also shed light on the physical properties of supernova remnants, such as their expansion rates and temperatures. The interaction between the remnants and the surrounding gas creates complex structures, including shock fronts and turbulent regions. Observations of GRBs can reveal how these structures form and evolve over time, providing clues about the energy released during the supernova explosion and the dynamics of the interstellar medium. Moreover, GRBs help scientists study the role of magnetic fields in supernova remnants. These fields can influence the behavior of the expanding gas, shaping it into intricate patterns and accelerating particles to high energies. By observing the polarization of light from GRB afterglows, researchers can map the magnetic fields within remnants and understand their impact on the surrounding environment. The significance of GRBs in studying supernova remnants goes beyond just understanding stellar death. These observations also provide insights into the broader processes that drive galaxy evolution. Supernova remnants are engines of cosmic recycling, dispersing heavy elements and energy into space, which can trigger the formation of new stars and planets. By studying GRBs and their connection to remnants, we gain a deeper appreciation of how the life and death of stars shape the universe. As we continue to explore the universe's most distant gamma-ray bursts, their role in illuminating supernova remnants reminds us of the intricate connections between stellar explosions and the cosmic landscape. Next, we'll turn our attention to one of the most energetic GRBs ever detected, GRB 080916c, and what it reveals about the extreme physics of these cosmic events. Stay with us as we uncover more secrets of the cosmos. Now, let's journey deeper into the cosmos to uncover the mysteries of one of the most extraordinary gamma-ray bursts ever recorded, GRB 080916c. Detected in September 2008, this event stands out as one of the most distant and energetic GRBs ever observed, offering a rare glimpse into the extreme physics of these cosmic explosions. GRB 080916c was detected at a staggering distance of approximately 12.2 billion light-years from Earth, meaning it occurred when the universe was just 1.8 billion years old. What makes this GRB particularly fascinating is its immense energy output. In just a few seconds, it released more energy than the Sun will emit over its entire 10 billion-year lifetime. This extreme energy release has led scientists to theorize that the burst was powered by a highly relativistic jet, a narrow beam of particles and radiation traveling at nearly the speed of light. The presence of such a jet is a key factor in explaining the burst's extraordinary brightness. As the jet interacts with the surrounding material, it produces shock waves that accelerate particles to incredibly high energies, resulting in the intense gamma-ray emission we observe. The jet's narrow focus also means that its energy is concentrated, making it appear even more luminous from our vantage point on Earth. This phenomenon, known as relativistic beaming, is a hallmark of some of the most powerful GRBs. But GRB 080916c didn't just break records for its energy and distance, it also provided critical insights into the nature of GRBs themselves. The burst's light curve, a graph of its brightness over time, revealed multiple peaks, suggesting that the jet may have been structured in layers or that the central engine, likely a newly formed black hole, underwent multiple episodes of energy release. This complexity challenges our understanding of how GRBs are powered and how their jets are formed. Another intriguing aspect of this GRB is its connection to the early universe. Because it occurred so soon after the Big Bang, it offers a unique window into the conditions of the cosmos during its formative years. The burst's light traveled through billions of years of cosmic history, carrying with it information about the density and composition of the intergalactic medium it passed through. By analyzing this light, scientists can learn about the universe's evolution and the processes that shaped its large-scale structure. The implications of GRB 080916c extend beyond just understanding GRBs. Its extreme properties push the boundaries of our knowledge of high-energy physics, testing theories about particle acceleration, magnetic fields, and the behavior of matter under extreme conditions. It also raises questions about the limits of energy release in the universe and the mechanisms that can produce such powerful events. As we continue to study GRB 080916c and other distant bursts, we are reminded of the universe's capacity for both beauty and violence. These cosmic explosions not only illuminate the darkest corners of space, but also challenge us to rethink our understanding of the fundamental laws that govern the cosmos. Next, we'll explore how gamma-ray bursts are helping us study the epoch of cosmic reionization, a pivotal period in the universe's history. Stay tuned as we uncover more secrets of the early universe. Now, let's turn our attention to one of the most transformative periods in the universe's history, the epoch of cosmic reionization. This era, which occurred roughly between 500 million and 1 billion years after the Big Bang, marks the time when the first stars and galaxies began to form, flooding the cosmos with light and ionizing the surrounding hydrogen gas. Gamma-ray bursts, with their incredible brightness and ability to act as cosmic beacons, are proving to be invaluable tools in studying this pivotal chapter of the universe's story. When a gamma-ray burst occurs, its intense flash of light travels through the vast expanse of space, passing through clouds of gas and dust along the way. As this light interacts with the intergalactic medium, it leaves behind a kind of fingerprint absorption lines in the burst's afterglow that reveal the properties of the gas it encountered. By analyzing these absorption lines, scientists can piece together the ionization history of the universe, tracing how the first stars and galaxies gradually transformed the cosmos from a dark, neutral state into the ionized universe we see today. One of the key challenges in studying cosmic reionization is that it happened so long ago and the light from that era is incredibly faint. This is where GRBs come in. Because they are so luminous, they can be detected even at extreme distances, allowing us to peer back in time to when the universe was still in its infancy. For example, GRBs like 080916c, which we discussed earlier, provide a snapshot of the universe just 1.8 billion years after the Big Bang, offering a glimpse into the conditions during the later stages of reionization. The afterglows of these distant bursts act like cosmic flashlights, illuminating the gas and dust that lie between us and the burst. By studying the absorption features in the afterglow's spectrum, scientists can determine how much of the hydrogen gas in the early universe was ionized and how this ionization changed over time. This information helps us understand the role of the first stars and galaxies in shaping the cosmos, as well as the processes that drove the transition from a neutral to an ionized universe. But GRBs don't just tell us about the ionization of hydrogen, they also provide clues about the distribution of other elements in the early universe. For instance, the presence of heavier elements like carbon and oxygen in the intergalactic medium suggests that the first stars were already seeding the cosmos with the building blocks of future galaxies and planets. This interplay between GRBs and the early universe's chemistry gives us a more complete picture of how the cosmos evolved during this critical period. The significance of GRBs in studying cosmic reionization extends beyond just understanding the past. By shedding light on how the universe transitioned from darkness to light, these bursts help us refine our models of galaxy formation and evolution. They also provide a unique testing ground for theories about the behavior of matter and radiation in the early universe, offering insights that are difficult to obtain through other means. As we continue to discover and study more distant GRBs, we are unlocking new secrets about the universe's formative years. These cosmic explosions not only illuminate the distant past, but also challenge us to rethink our understanding of the processes that shape the cosmos. Next, we'll explore the intriguing possibility of gamma-ray bursts occurring within our own galaxy and their potential impact on Earth. Stay with us as we delve into this fascinating topic. Now, let's shift our focus closer to home and consider the possibility of gamma-ray bursts occurring within our own galaxy, the Milky Way. While most GRBs we observe come from distant corners of the universe, the question arises, what if one happened right here in our cosmic neighborhood? The implications are both fascinating and sobering. Gamma-ray bursts within the Milky Way are rare but not impossible. In fact, scientists estimate that a GRB could occur in our galaxy roughly once every few 100,000 to a million years. This might sound like a long time, but on a cosmic scale, it's a blink of an eye. The real concern lies in the potential impact such an event could have on Earth. If a GRB were to occur within a few thousand light-years of our planet, the effects could be catastrophic. The intense burst of gamma rays could strip away Earth's ozone layer, exposing life on the surface to harmful ultraviolet radiation from the sun. This could lead to mass extinctions and disrupt ecosystems on a global scale. However, before we sound the alarm, it's important to consider the protective role of our galaxy's structure. The Milky Way is a vast spiral galaxy with a dense central region and sprawling arms filled with stars, gas, and dust. Most GRBs are thought to originate in regions of intense star formation, which are more common in the galaxy's outer arms. Earth, located in a quieter, less densely populated region of the Milky Way, is somewhat shielded from the most active areas where GRBs are likely to occur. Additionally, the vast distances between stars in our galactic neighborhood reduce the likelihood of a nearby GRB. But what if a GRB did occur closer to home? The good news is that the probability of such an event is extremely low. Even if a GRB were to happen within the Milky Way, the chances of it being close enough to cause significant harm to Earth are minimal. Still, studying the distribution of GRBs within our galaxy helps us better understand their origins and the conditions that lead to these powerful explosions. It also provides valuable insights into the broader question of how GRBs are distributed across the universe. The connection between GRBs and the Milky Way also highlights the importance of our galaxy's structure in shaping the cosmic environment. By studying where GRBs occur within the Milky Way, scientists can gain a deeper understanding of the processes that drive star formation and the evolution of galaxies. This, in turn, helps us piece together the larger story of how the universe has evolved over billions of years. As we continue to explore the mysteries of gamma-ray bursts both near and far, we gain not only a better understanding of these extraordinary events, but also a greater appreciation for the delicate balance that allows life to thrive on Earth. Next, we'll turn our attention to how GRBs can be used to study the atmospheres of distant planets, offering new insights into the search for life beyond our solar system. Stay with us as we uncover this exciting frontier of cosmic exploration. Now, let's venture into an exciting new frontier where gamma-ray bursts meet the search for life beyond our solar system. Gamma-ray bursts, or GRB, aren't just cosmic fireworks. They can also serve as powerful tools for studying the atmospheres of distant exoplanets. When a GRB occurs, its intense flash of light travels across the universe, and if it passes through the atmosphere of an exoplanet, it leaves behind a unique fingerprint. This fingerprint, known as an absorption spectrum, reveals the chemical composition of the exoplanet's atmosphere. By analyzing these absorption features in GRB afterglows, scientists can detect the presence of gases like oxygen, methane, or even water vapor, key ingredients that could hint at the possibility of life. However, using GRBs to study exoplanet atmospheres isn't without its challenges. One major hurdle is timing. GRBs are fleeting events lasting only seconds or minutes, and their afterglows fade quickly. This means telescopes must be ready to observe the burst almost immediately after it occurs. Additionally, the exoplanet must be perfectly aligned between the GRB and Earth for its atmosphere to leave a detectable signature. This alignment is rare, making such observations a game of cosmic luck. To overcome these challenges, scientists rely on a network of space-based telescopes like Swift and Fermi, which can rapidly detect and pinpoint GRBs, as well as ground-based observatories that can quickly follow up with detailed observations. Another challenge lies in interpreting the data. The absorption features in GRB afterglows are incredibly faint, and distinguishing them from other sources of interference requires advanced techniques. Scientists use sophisticated models and algorithms to isolate the signals from exoplanet atmospheres, ensuring the results are accurate and meaningful. Despite these difficulties, the potential rewards are immense. By studying the atmospheres of exoplanets through GRBs, we can gain insights into their habitability and even identify potential biosignatures, chemical markers that could indicate the presence of life. The significance of this approach goes beyond individual exoplanets. It opens up a new way to explore the diversity of planetary environments across the galaxy. GRBs act as cosmic flashlights, illuminating the atmospheres of worlds that would otherwise remain hidden in the darkness of space. This method complements other techniques, such as transit observations and direct imaging, providing a more complete picture of exoplanet atmospheres and their potential to support life. As we continue to refine our techniques and expand our understanding of GRBs, their role in the study of exoplanets will only grow. These powerful cosmic events are not just windows into the most energetic phenomena in the universe. They are also keys to unlocking the secrets of distant worlds. Next, we'll delve into the mystery of GRB 090510, a short burst that challenged our understanding of the fundamental laws of physics. Stay tuned as we explore this groundbreaking discovery. Now, let's turn our attention to a gamma-ray burst that not only captivated scientists but also challenged the very foundations of modern physics. GRB 090510, detected in 2009, was a short burst that lasted just a fraction of a second, but its impact on our understanding of the universe was anything but fleeting. What made this event so extraordinary was the evidence it provided for something called Lorentz invariance violation, a concept that could reshape our understanding of space, time, and the laws of physics. Lorentz invariance is a cornerstone of Einstein's theory of relativity, which states that the laws of physics are the same for all observers, regardless of their motion. It's a principle that has held up under countless tests until GRB 090510 came along. Observations of this burst revealed that high-energy photons, or particles of light, arrived at Earth slightly later than lower-energy photons, even though they were emitted at the same time. This tiny delay, measured in milliseconds, suggested that space-time might not be as uniform as we once thought. In other words, the fabric of the universe could behave differently at extremely high energies, potentially hinting at the existence of quantum gravity, a theory that seeks to unify Einstein's relativity with the strange world of quantum mechanics. The implications of this discovery are profound. If Lorentz invariance is violated, it could mean that our current understanding of physics is incomplete, and that there's a deeper layer of reality waiting to be uncovered. Quantum gravity, which remains one of the greatest unsolved problems in science, could hold the key to explaining phenomena like black holes, the Big Bang, and the nature of space-time itself. GRB 090510 provided a rare glimpse into this mysterious realm, offering a tantalizing clue that could guide future research, but the mystery doesn't end there. The detection of Lorentz invariance violation also raises questions about the nature of gamma-ray bursts themselves. Could these cosmic explosions be natural laboratories for testing the limits of physics? And if so, what other secrets might they reveal about the universe? While GRB 090510 has given us a lot to ponder, it's also a reminder of how much we still have to learn. As we continue to study these enigmatic events, we may find that they hold the answers to some of the biggest questions in science. Next, we'll explore how gamma-ray bursts are helping us unravel the mysteries of cosmic magnetic fields, shedding light on the invisible forces that shape the universe. Stay tuned as we dive into this fascinating topic. Now, let's shift our focus to another fascinating aspect of gamma-ray bursts, their role in unraveling the mysteries of cosmic magnetic fields. These invisible forces woven throughout the universe play a crucial role in shaping galaxies, stars, and even the paths of cosmic rays. But how do we study something we can't see? Enter gamma-ray bursts, which act as cosmic flashlights, illuminating the magnetic fields that lie in their path. When a gamma-ray burst occurs, its afterglow, the lingering light that follows the initial explosion, travels through vast stretches of space. As this light passes through regions with magnetic fields, something remarkable happens. The magnetic fields cause the light to become polarized, meaning its waves align in a specific direction. This polarization can then be measured using a phenomenon called Faraday rotation, where the orientation of the light's waves twists as it interacts with the magnetic fields. By analyzing this twist, scientists can determine the strength and distribution of the magnetic fields the light has encountered. This technique has provided groundbreaking insights into the nature of cosmic magnetic fields. For instance, it has revealed that these fields are not uniform but vary widely in strength and structure across different regions of the universe. Some areas, like the cores of galaxies, host incredibly strong magnetic fields, while others, such as the vast voids between galaxies, are nearly devoid of them. Understanding these variations helps us piece together how magnetic fields influence the formation and evolution of cosmic structures. But the significance of gamma-ray bursts in this field goes even deeper. By studying the polarization of GRB afterglows, researchers can also probe the origins of these magnetic fields. Are they remnants of the early universe generated during the Big Bang? Or are they created by the turbulent motions of gas and plasma in galaxies and galaxy clusters? GRBs offer a unique window into these questions, providing data that other astronomical phenomena simply cannot. The implications of this research are profound. Cosmic magnetic fields are not just passive features of the universe, they actively shape the behavior of matter and energy on the largest scales. They guide the movement of charged particles, influence star formation, and even play a role in the acceleration of cosmic rays. By using gamma-ray bursts to study these fields, we're gaining a clearer picture of how the universe operates at its most fundamental level. As we continue to explore the role of gamma-ray bursts in understanding cosmic magnetic fields, we're reminded of how interconnected the universe truly is. These bursts, born from the most violent events in the cosmos, are helping us decode the invisible forces that govern everything around us. Next, we'll delve into how gamma-ray bursts might even hold clues to one of the greatest mysteries of all, dark matter. Stay tuned as we uncover the next chapter in this cosmic detective story. Now, let's turn our attention to one of the most intriguing possibilities in gamma-ray burst research, their potential connection to the search for dark matter. Dark matter, the mysterious substance that makes up about 85% of the universe's mass, has eluded direct detection for decades. But what if gamma-ray bursts could help us uncover its secrets? One theory suggests that dark matter particles, when they collide or decay, could produce gamma rays. These gamma rays would then be detectable within the spectra of gamma-ray bursts. By carefully analyzing the light from GRBs, scientists hope to find subtle signatures that could point to the presence of dark matter. For example, if dark matter particles annihilate or decay, they might release gamma rays at specific energy levels. These energy signatures, often referred to as lines, could serve as fingerprints of dark matter hidden within the broader gamma-ray emission of a burst. However, this approach is not without its challenges. The gamma-ray spectra of GRBs are incredibly complex, filled with signals from various astrophysical processes. Distinguishing a potential dark matter signal from this background noise requires precise measurements and advanced data analysis techniques. Additionally, the exact properties of dark matter, such as its mass and how it interacts with other particles, are still unknown, making it difficult to predict what these signatures might look like. Despite these hurdles, researchers remain optimistic. Gamma-ray bursts, with their immense energy and ability to illuminate the farthest reaches of the universe, provide a unique opportunity to probe dark matter in ways that other methods cannot. For instance, the high-energy gamma rays produced by GRBs could interact with dark matter particles in ways that reveal their presence, even if only indirectly. This makes GRBs a powerful tool in the ongoing quest to understand one of the universe's greatest mysteries. The search for dark matter using gamma-ray bursts is still in its early stages, but the potential rewards are immense. If successful, it could not only confirm the existence of dark matter, but also shed light on its properties and role in the cosmos. As scientists continue to refine their techniques and analyze more GRB data, we may be on the brink of a groundbreaking discovery that reshapes our understanding of the universe. With this tantalizing possibility in mind, we now move to our final fact, where we'll explore how gamma-ray bursts are shaping the future of astronomy and what exciting discoveries may lie ahead. Stay with us as we wrap up this cosmic journey with a look at the role of GRBs in the next frontier of space exploration. As we step into the final chapter of our exploration, let's look ahead to the future of gamma-ray burst research and its transformative potential for astronomy. Gamma-ray bursts, with their unparalleled energy and ability to illuminate the farthest corners of the universe, are poised to remain at the forefront of cosmic discovery. But what makes them so crucial for the next generation of astronomical breakthroughs? One of the most exciting developments is the advent of next-generation telescopes and observatories. Instruments like the James Webb Space Telescope, the Vera-C, Rubin Observatory, and the upcoming Cherenkov Telescope Array are set to revolutionize our ability to study GRBs in unprecedented detail. These advanced tools will not only capture gamma-ray bursts with greater precision, but also allow us to observe their afterglows across multiple wavelengths, from X-rays to radio waves. This multi-messenger approach will provide a more complete picture of these cosmic explosions, revealing insights into their origins, environments, and the physics driving them. But the potential of GRBs goes beyond just understanding the bursts themselves. They serve as cosmic lighthouses, illuminating the distant universe and allowing us to study the earliest epochs of cosmic history. By analyzing the light from GRBs, scientists can probe the conditions of the early universe, trace the formation of the first stars and galaxies, and even test fundamental theories of physics, such as the nature of space-time and the speed of light. In this way, GRBs are not just fleeting flashes in the sky, they are windows into the very fabric of the cosmos. Another promising avenue is the integration of GRB research with other fields of astronomy, such as gravitational wave detection and neutrino observations. The groundbreaking detection of GRB 170817A, which coincided with gravitational waves from a neutron star merger, marked the dawn of multi-messenger astronomy. Future discoveries like this could unlock new insights into the nature of neutron stars, black holes, and the extreme environments where these objects collide. As we look to the future, the possibilities are truly limitless. Could GRBs help us uncover the secrets of dark energy or reveal the existence of exotic particles? Might they provide clues about the conditions necessary for life to emerge in the universe? These are just some of the questions that drive researchers forward, fueled by the promise of new technologies and the boundless curiosity that defines astronomy. Gamma-ray bursts have already reshaped our understanding of the universe, and their role in the future of astronomy is set to be even more profound. With every new discovery, we move closer to unraveling the mysteries of the cosmos, one burst at a time. As we conclude this journey through 50 fascinating facts about the universe's most distant gamma-ray bursts, we invite you to stay curious, keep exploring, and join us as we continue to uncover the wonders of the universe. Don't forget to like, subscribe, and hit the notification bell so you never miss out on the latest cosmic revelations. Until next time, keep looking up. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible insights we've uncovered about the universe's most distant gamma-ray bursts. From their accidental discovery in the 1960s to their role as cosmic lighthouses illuminating the early universe, GRBs have proven to be one of the most fascinating and powerful phenomena in the cosmos. We've explored how these bursts, born from the collapse of massive stars or the collision of neutron stars, release energy on a scale that defies imagination, enough to outshine entire galaxies in mere seconds. We've delved into the mysteries of their afterglows, which provide a treasure trove of information about the environments they originate from, and how they've helped us probe the farthest reaches of space and time. GRBs like GRB 090423, detected 13 billion years ago, have offered us a glimpse into the universe's infancy, just 630 million years after the Big Bang. These bursts have not only deepened our understanding of stellar life cycles, black holes, and neutron stars, but have also opened doors to testing fundamental theories of physics, such as relativity and the nature of spacetime. Yet, for all we've learned, gamma-ray bursts remain shrouded in mystery. Why do some GRBs lack visible afterglows? What exactly powers the ultra-long bursts that last for hours or even days? And could these cosmic explosions hold clues about dark energy, dark matter, or even the conditions necessary for life to emerge in the universe? These questions continue to drive astronomers forward, fueled by the promise of next-generation telescopes and the ever-evolving field of multi-messenger astronomy. As we stand on the brink of new discoveries, one thing is clear: gamma-ray bursts are more than just fleeting flashes in the sky. They are keys to unlocking the secrets of the cosmos, offering us a deeper understanding of the universe's past, present, and future. So, whether you're a seasoned space enthusiast or just beginning to explore the wonders of the universe, we invite you to stay curious and keep looking up. If you've enjoyed this journey through 50 fascinating facts about gamma-ray bursts, don't forget to like, subscribe, and hit the notification bell so you never miss out on the latest cosmic revelations. Together, let's continue to uncover the mysteries of the universe, one burst at a time. Until next time, keep exploring.